the server mount zoom across the system, sometimes it has technical issues. Yeah. So
well, let's hope not.
Okay, looks good on my end.
So I know that some people have joined, right? Who are supposed to.
Yeah, so I'll be monitoring the attendee list, and
Okay.
If we do see people supposed to be on the panel, I'm gonna promote them. I see Norm is here.
Okay, then I think I should start to ask some questions.
Hi, Danny.
Hey, good morning.
You've got a colorful background.
Those are adiabatic shear bands in electromagnetically collapsing cylinders.
Oh, nice.
Wow.
I like instabilities.
Yes.
Yeah, Daniel, I remember this background when John Hutchinson was presenting the, is it the same? The first EML webinar. Is this the same background that you were using?
No, this is our work. I don't think John has seen them ever, but no, I don't know. This is our work.
Some virtual background some people used, a very colorful and circular shape.
Yeah. This is a little bit of outwork, but basically what you see is the fragments. I mean, the collapsing cylinders are those things, and what's in the center is just a kernel to stop the collapse. The whole experiment takes 2 microseconds, and it digests 1 megawatt of electromagnetic power.
Oh.
It's a violent experiment, but we could count fragments, analyze shear bands, and understand all kinds of things. So.
Hi, Norman. Really good to see you.
Norman, you're muted.
Hi, Li Ching.
Hi.
So, greetings from I'm an exile on the island of Madeira. It reminds me of Napoleon, who committed a crime and ended up in Elba. My crime was to use British Airways.
Norman, no, you just decided to skip the British autumn.
Okay, yeah. I'm just stepped out of the ocean where the temperature was chilly at 20, so.
Okay, let me start an informal interview to Vikram. Yeah, Vikram, I know you got your bachelor degree from India. Then you went to UK, then you came to US, went back to UK again. Yeah, can you briefly introduce your academic journey all the way to today?
Well, I was a mechanical engineer at IIT Bombay. And then I came to Cambridge with the intention of being here for only 1 year to do a master's. But it ended up being much longer than anticipated. And I didn't really start working in sort of the area that I'm working in, right? I joined what they call the vehicle dynamics group there. But I sort of slowly migrated into materials rather than vehicle dynamics. And then that's how I started meeting Norman Fleck and Mike Ashby, who had a great influence on me, of course. And after that, I was with Alan Needleman. After my PhD, I went and worked with Alan Needleman at Brown, which was a very interesting experience because my background was primarily experimental. And Alan, as you all know, right, is the numerical guy, so you have to get in front of the computer and write code. And it was very interesting. But I learned a lot. We really learned, a lot with him. And then I came back for faculty and in Cambridge, and worked a lot with people like Bob McMeeking, Tony Evans in those days, John Hutchinson, and I was at Santa Barbara, and then I came back to Cambridge, and that's sort of, and that's the sort of, in some ways, it's followed various problems and worked with different people on different problems, really. But my experience, of course, at both Brown and Santa Barbara were very exciting. They were short times, but they were very exciting.
Great. Yeah, I know you started to work on architecting materials very early on, like late 1990s.
But yeah, that's when actually it all started, when Tony Evans was at Harvard in those days, I think.
Right, Harvard, MIT, right?
Yeah, I mean, maybe Princeton or Harvard. I'm not exactly sure where Tony was in those days, but that's when I was working with Norman Fleck and and Tony and people like. That's how the work on architecture materials started. But it morphed into various things, really. It went from materials to applications, which was really a good thing of what Tony Evans taught us all, that think of applications driving development of materials. I mean, you can do it both ways. You can say, I just come up with materials and find applications, or you can think of it the other way around.
Hey, Vikram, this is Sulin from Penn State.
Hi, Sulin.
I heard a long time ago that Santa Barbara was about to bring you to Santa Barbara, UC Santa Barbara. I heard that news, but I don't know why you didn't come.
I was there. Sulin, I was at Santa Barbara, for 2 years on the faculty, but then I came back.
Oh.
So you may have missed me. My period at Santa Barbara was short enough that you may have missed it.
Okay. So you don't like that place, huh?
No. I wouldn't say that at all, basically. Other than the fact, of course, that people like Lihua have to wake up at 6:30 in the morning for an EML seminar.
Yeah.
Okay. Vikram, when were you in Santa Barbara? Which year?
2006 to 2008, maybe a bit later than that.
We did not overlap.
No, Shigang. They wouldn't have taken me while you were there. They would have had better people.
Zhigang, have you started recording?
Oh, Jesus. I started to go to, yeah.
YouTube, yeah. So you have YouTube. Yeah, but your virtual looks very interesting today.
Stop live. Yeah, somehow, recording, yeah. Recording to cloud. Thank you. Recording to cloud. But it's streamed on YouTube.
Yeah, then Vikram, late 1990s, the experimental and fabrication capability of architecting material must be very limited. But right now, because of the new development of all those manufacturing technology, can you talk about the environment of working on architecting material then, and what are the things you were not able to do you can do right now?
In some ways, in those days, Norman can say a lot too about it, is that I think at least the way we were thinking about it is only things we could make. We were, you weren't thinking openly about architecture, because so things we were making were things by investment casting and injection molding and things like that, industrial techniques. There was, I shouldn't say that there was no it was called rapid prototyping in those days rather than 3D printing, but essentially it was the same thing. But the technology was far less developed. So you would not be able to make large pieces of material with complex architectures by those rapid prototyping methods. And nobody would have even considered them to be sort of the rapid prototyping techniques were for making components. They were not for making materials. That is, I think, the difference that has happened with 3D printing today, that you can consider making materials by those methods. And none of the work that, Lucas is here, so none of this work on nano and micro was possible in those days. So it was really rather different. You thought what was your manufacturing constraint, and that was defining it. But very quickly it morphed to from materials to structures, in the sense of saying that you're going to use these architectures in sandwich structures. And so it very quickly morphed into saying that we are just going to think about structures rather than materials in general, really. Because it was application driven to some extent, not completely, but to some extent at that time. I think that is the big difference today, right? People are really thinking about it as materials in general, and thinking of them as materials without, a specific application in mind, at least at the moment.
Right. Yeah, and the scale people can go is much down, so that you can really think about them as a material.
Yeah, that's right. I mean, there are, of course, massive challenges about scaling it up into an engineering scale. But, I think there are the applications like in shoe soles and things like that are already there, right? I mean, people are using those kinds of things extensively.
Yeah,
I guess, Vikram, it's still an issue when, it's still an issue in designing. At what point do you design strut by strut? So for a shoe, so Adidas or Nike will probably design strut by strut. But if it's a ship sandwich structure, then you think of it as an effective medium core. And I guess with the additive manufacture, it's sort of, well, I think it's more towards thinking of it as a structure than thinking of it as a material. What do you think? Yeah.
Absolutely. I mean, it's in some ways, I think in lots of current applications, I think they're more like structures rather than materials, like, these shoe soles and ship structures, etc. Right? You'd hardly think of them as materials. And there's another big difference I should point out, which has happened. And Ole Sigmund gave I thought was a wonderful EML seminar, is that these techniques to optimize for specific applications have gone so far, basically, which I think have opened, I mean, that to me is the big thing, right? That, you have to if you can make something, but if you don't know what to make, then, you're not going to go far, basically. But the fact that you can do some kind of optimizations, and some people will say you can now do machine learning on that as well, basically, and there are papers coming out on that. But one way or the other, you can actually do the inverse problem. And that, to me, is very critical, to invert from, as an engineer, what is the material property, stress strain curve, whatever, toughness, whatever you want. But that does, to go back to architecture is a very different story, basically, from those highly nonlinear material properties to architecture.
Hey, Jimmy is here.
So I have a couple of questions on that. So I think I agree with Dharma. I don't know where that line is between now materials and structures, because it gets blurred for me. Because yeah, like for the Adidas shoe, it's like 2 layers of a lettuce. Like it's almost just a sandwich structure at that point. And so I'm curious to see where you think that line is, if there is one, or if there's just kind of a continuous transition between something as a structure or something as a material.
Well, in some ways, there is the, homogenization definition. If you say that the gradients of the imposed deformation are, if those length scales associated with that are large compared to the microstructural length scale, you can think of an effective medium. Otherwise, an effective medium doesn't mean anything, really. And as you said, in the Adidas shoe, it makes no sense. In lots of these sandwich ship structures, also it makes very little sense to think of them as effective mediums, basically. It's going to be interesting to know whether, in which cases, there are very few examples that come to my mind where we are using these as materials at the moment.
Yeah, then Vikram, I know detecting material is just one aspect of your research. You also do a lot of other things. For example, cell mechanics, or biomechanics. Yeah, can you talk about like your research interests and how you were led to very different fields?
Well,
your research interest evolves.
There is no answer to that other than if something catches like all of us, right? If something catches your imagination, you will follow your nose, basically. And that is, mean, I will give one thing which I will say, and it's true for big US universities as well, of course, in the ones that I've been at, is that a big advantage in Cambridge is that nobody tells you what to do, and it has its pluses and minuses, but there's enormous freedom, which means that some people will say you've not gone deeply into anything, but I will say that I've had fun. So in some ways, I'll say that the stuff in bio which interests me most is this coupling between biochemistry and mechanics. I mean, we saw Zulden's talk last week. There's such fantastic problems in mechanics at the interface between chemistry, biochemistry, and mechanics that it would be difficult for somebody who is really interested in mechanics to ignore those problems today, basically. And with the measurement technologies that are coming along, which means it's become quantitative. It's become so quantitative that people like us, I think, can really have, do something in it.
Hey, Vikram, I like your comments very much.
Yeah, Sulin just gave a talk last week. Cell mechanics.
Yeah, I heard that. I do. As you remember, one time I don't remember where we have a very little conversation about how we're interested in doing biomechanics, mechanobiology thing.
Yeah, I mean, I think mechanobiology. The issue, of course, I'm sure you will sort of agree, is that while we mechanics people find enormous interesting problems, it's to make an impact on the cell biologists to say that we can actually do something which they find of use is something that at least people like me have always struggled with. That, we do something, it's rather cute, it's fantastic, it's good science, but in some ways, a lot of the people I speak to, they say, yeah, but I knew this from the experiment already. So it's always a question of what is it that we can tell them, which they would not have otherwise known, basically, which is
exactly.
And that is a very difficult question, basically.
Most people doing mechanobiology are from biology side, not from mechanics side.
Yeah.
There are a lot of mechanics there that need to be straightened out, I think.
But there is some analogy in early days, I suppose, when mechanics people want to do material science problems, right? When you first discover dislocations, so a little bit of history of dislocation, I read, it was first discovered on theoretically, right? Postulate the existence of dislocation, and Taylor even predict string hardening from mathematics of elasticity. So at that point, I guess his dislocations probably had very little relevance to the strength of steel. But over the time, by the time Arriaga, Hutchinson, Rice, then the connection between materials and mechanics were really forged. Norman, do you have the similar sense?
Yeah, I mean, I think what I'm interested in this discussion is a common language, because in mechanics and materials, in a sense, they were different communities, but they progressively were brought together, and it became a community of people in the mechanics of materials area. What I don't know in the mechanobiology area is whether that will happen, because there's such a difference in the language of biology from the language of mechanics. And what I don't really know, and so I'm intrigued, for example, whether in the biophysics community that that sort of common crossbreeding has led to a shakedown state where people are equally comfortable, on the bio side and the physics side, or is there? I get the impression there's still that tension, or two different communities. There's the sort of physics end and the biological end, and they're very far apart. So
I think so, Norman. The reason I think
actually the statement you made years ago, Norman would know this, when the mechanics people started to work on materials, they essentially, the materials people made the same statement, saying that whatever you discovered, we knew it long ago. It's not something new, right?
I think
Yeah, I like to joke with this because my PhD was experimental fatigue, and so I knew all the fatigue people. And I used to say to material science people, when they thought about fatigue or thought about dislocation theory, they were constructing a sort of religion where they invented new words and new stuff. And then you say, well, surely you can do a calculation to show if that's right or wrong. And they say, oh, no, it's much more complicated than that. So I think the way these things emerged is some of the mystique is gradually being taken out of some of these subjects like dislocation theory or like biology or fatigue. And it ceases to have the almost made up random. I mean, hydrogen embrittlement is a good one that Vikram can speak to, where there's for every person, there are at least 2 theories of hydrogen embrittlement, and 99% of them don't make any sense. But if you say that, they'll just come up with another theory that doesn't make any sense. So that's where mechanics can contribute, I think, as being an honest arbitrator of ideas.
I think that is true, but the problem, which at least when I talk to real biologists, is you see in materials there might be maybe 5 phenomena that are governing some observation. Typically in biology there might be 50 things happening at the same time that are governing, that are going on in that controlled experiment of yours. Forget something that is happening in vivo, just in your controlled experiment. And that is the issue that we face in modeling, that how many phenomena are we capable of actually including in our sort of analysis, really. And that is a major problem in biology, because there are too many things happening, really, at the same time.
Yeah, I remember quite a few years ago, Subra Suresh was giving a speech over the dinner of one of the major mechanics conferences. I don't know any of you were in that audience. That's when he was in the early years, when he was probably still working on the biomechanics of the malaria infected blood cells, right? So he was sharing his experience talking to the physicians and biology people. And I remember he said that at the very early beginning, it's super stretch, right? So in our field, it's a giant over there. When he was trying to talk to the physicians and also the biology people, they were like, what are you doing in our backyard? So I think like Norman mentioned, it's in the early stage, the challenge could be these 2 group of people are talking in 2 different languages. Like Vikram mentioned, right? There were like probably 50 things ongoing in vivo over there. And we are trying to chip in our insight or understanding from the mechanics or even with some material science language. But even for that, trying to communicate and talk to the people in biology is not that easy. I mean, eventually, for example, after quite some years, and then Subra and then and with the colleagues and showed us and showed them that this has something to do with the mechanics, but this entry barrier is actually quite high for more junior people. I think that's even a bigger challenge over there. Still there. I guess probably Sulin has more saying about this. So.
But it's a rich problem. I mean, there's no question.
It is. Yeah.
But I think, these things happen whenever we mechanics people try, I mean, Shigang can say, right, when you start going to batteries, electrochemistry, I'm sure there were barriers to even trying to talk to electrochemists, right? These barriers exist whenever you try to cross fields, basically.
Yeah, I think mechanics people are doing very well in the electrochemistry world nowadays, right? And they really appreciate that their problems largely comes from the mechanics failure of their electrode interfaces between electrode and electrolyte and things like that. Yeah, that's another excellent example of what mechanics can do nowadays.
In the biology area, I think the ultimate application area is medicine, right? And in the medicine, the bottom line is whatever the biologists do, the biochemists do, the pharmacologists do, does it help a cancer patient? Or does it heal a nephrology, right? But the whole field of medicine is so much based on statistics. It's not so much first principle based, right? It's almost like, does this drug work? Okay, they always ask the question, have you tested 10,000 patients? Right? What is the FDA approval requirements? But material science is more physics based, right? It's more reductionist approach. The techniques, the tools, the questions may be different, but the underlying physical science is the same. Physical science mentality of thinking since the Enlightenment. If you think of biology, the DNA was discovered only in 50s, which connects something fundamental related to life. So it's like Newton's laws was discovered, in 1600s, and 400 years later came, or 300 years later came, the DNA. So it would need lot more time for the biologist, medicine to think in terms of reductionist approach. Right? What is the cause? Yeah. So yeah, mechanics, we always think in terms of input-output relationship, a predictive capability. Biology is related to 10,000 patients, 30,000 infectious disease people. Vaccine takes months, years. That's a big barrier.
Absolutely.
Okay, it's almost the time. Yeah, Vikram, can I ask you to share your screen?
Sure.
Yeah, we will have exciting discussion after the lecture as well.
So I can't yet share my screen because host has not allowed me to.
Vikram, it's good to see you. I would have to leave for my class soon. So I thought I joined a bit earlier.
Wonderful to see you, Tahir. Thank you.
Yeah, maybe while we are waiting, let me start to introduce Vikram.
Or should I make?
Okay, yeah, we can see your screen now. Good morning, good afternoon, good evening. This is Lihua Jing. I'm an assistant professor from UCLA. It's my honor to introduce our speaker today, Professor Vikram Deshpande from the University of Cambridge. Professor Vikram Deshpande joined the Faculty of Engineering at the University of Cambridge as a lecturer in 2001 and was promoted to a professorship in materials engineering in 2010. He has written more than 270 journal articles in experimental and theoretical solid mechanics. He serves on the editorial boards of a number of journals in mechanics and biomechanics, including JMPS, Modeling and Simulation in Material Science and Engineering, and the Proceeding of the Royal Society, London. He has been awarded the Philip Leverhulme Prize, the William Hopkins Medal, the 2020 Ronnie Hill Prize in Solid Mechanics, and elected as Fellow of the Royal Society, London. So today he's going to talk about ballistic and blast response of structural materials, lessons from architecting materials. Without further ado, Vikram, the floor is all yours.
Thank you very much, Liu, and thank you to the organizers of EML for inviting me. This is both a pleasure and honor. Very illustrious mechanicians have come before me, including John Hutchinson to start off with. So this is, I hope I can say something that you might learn something, but I'm not sure of that. Okay, so what I'll talk about today is work, which I've done over a few years. A lot of this work has been done in collaboration with Hayden Wadley and Norman Fleck, who I have to give a lot of credit to for many of the ideas, and a number of students and postdocs who I have listed here. Some of them who are here, some of them are, have moved on, etc. And some of them who are present in the audience right now. So so what is it that I'm going to be talking about today? And I'll start off, because I'm from Cambridge, with something that Ashby had done, a beautiful chart. Effectively, he was correlating the history of human development with making material, with new materials. And I'll talk stronger because that will be something of a theme in the talk today. So what he's showing here is the typical Ashby plot of strength against density. And in prehistoric times, these were the materials, essentially only natural materials, and the only metal were the ones occurring in their natural state. This is the peak of the Roman Empire. And what you can see is that suddenly there are many more metals, especially which have, which is what, as we know, the Romans did great engineering with. And then if you go to 1,000 more years, very little had changed. So from 50 BC to 1500 AD, not much had changed other than iron had, some cast iron had come in. In another 400 years, you had added steel, which is a very big thing. And then by end of World War II, you had added some aerospace alloys, polymers had started to come in. And this is what approximately exists today as engineering materials. And the main thing you can see is these low density foams and architected materials that have started coming in. So there's this sort of correlation between human development and designing of materials. And that has continued. And of course, modern days, you judge it by what science, nature papers you have. So there's plenty of papers that are coming on which is the strongest, lightest material that you can make. And this is an Ashby plot, and effectively there are certain parts of the Ashby plot which cannot be attained. There are no materials that can ever be made there by bounding theorems. You can say that you can't go out here. But there's lots of places where there are materials which don't exist, but in principle materials could exist. For example, the Hashim-Strickman bound with diamond as the starting point will tell you that a material in principle could exist along here, not that it has been made or we know how to make such a material. So there have been lots of papers coming out with that, and mainly nano micro, as we were having in this discussing earlier on. And for example, I'm showing you some of the very early papers. These were all by Julia Greer, to be honest, where they made nano materials using things, and they're sitting on the Ashby plot. Norman Fleck in his seminar spoke about gyroids, and this is where the gyroids will be sitting. And then there are papers which are coming out from those nanoscribes in the Karlsruhe group, and they're making materials, some of them, which like this structure here, which are truly getting into this kind of space here in the Ashby plot. So the question, and there are 100 other papers, which I apologize for not citing, where people have made lots of new materials, which I have not spoken about here. I'm sure there are other materials lying here too. So, but that's not the aim of this talk. The aim of this talk is saying that suppose you can make these materials, what is it that you can do with these materials? And I'm going to speak about one very specific application. There could be lots of application to say that if you could make such materials, what would you gain? And the application that I'm going to be discussing is mitigation against dynamic loads, because that, if you want to make strong materials, that's an obvious application, right? You think if you have something strong, it will work well for these kinds of dynamic loads. So this is our structure. And there are two types of loads. You can have some buried explosive coming and hitting the structure, and sort of a granular high velocity medium coming in, or you can have some kind of explosive and you have fragments coming from the side here like that. So these are the two applications I will be discussing. So protection against high velocity granular impact, and we'll think of sandwich structures with some kind of architected cores, which will help, and lots of different sandwich structures with different architectures. And similarly, protection against high velocity projectiles. What is it that you need? What kind of material properties really do you need to protect against high velocity projectiles? And the question, the underlying theme of the whole talk is high strength what you need for such applications? Now, you might say that that's pretty obvious, that obviously I need high strength. And I hope to convince you by the end of the talk that yes and no is the answer to it, is that it's not absolutely clear that high strength is always good, basically, okay? So that's going to be the aim. Okay, so let's start off with the first application, which is this against high velocity granular impacts, really. So whenever we talk about granular impacts, there are two problems, and this occurs all the time with dynamic loads, is that you have to understand how the loading was created on your structure. So we need to understand the interaction between the explosive, the granular medium, and the ambient air around it. And then, of course, we need to understand how the high velocity medium is going to interact with the structure. So this is an experiment where you basically have some explosives surrounded by some particles, and if you sort of do the detonation, this is what you get. So what you see is that you can see these jets forming. And this formation of jets is known in lots of examples in volcanic eruptions. That's how you spread the ash much further than if you just had a simple explosive kind of event. And it's remarkable, actually, how little is understood about why these jets form, how these jets form, etc. So we're going to first understand very quickly what is this explosive granular medium ambient air interaction? And think of a very simple experiment. My whole seminar will be sort of talking about very simple experiments, okay, to try to understand these complex phenomena, and may or may not succeed in that, of course. So you put a sand slug in a polycarbonate tube, and you have a high pressure cylinder here like that, and you let that high pressure gas come out, and it will accelerate the sand slug. And let's see what happens. So that's the aim here. Okay, so this is dry sand. It's perfectly dry. It's been colored to just help us understand what's happening. And that high pressure air comes from the back, and it goes through like that, and it's all stable, very nice, nothing happens. It's just accelerating. This is a high-speed video, so it's going very fast, but it's pretty stable. Now you do that with water. If you water saturate the granular medium, this is what happens. Immediately, nearly on this rear surface, you get an instability forming, and you can see what's happening. Some kind of mixing and instability is forming, but the front is remaining pretty stable, really. So first, I'm not yet gone to the jet formation. Can we actually understand why this is happening? Can you do a really very simple simulation to understand what's happening? So this is my granular medium. It's described by a very simple, isotropic Drucker-Prager kind of solid. So what do I mean by Drucker-Prager solid? That it has some pressure dependency to its yield strength, and its pressure dependency is denoted by the friction angle, typical for a granular medium. But I'll assume non-associated flow, so that means the granular solid remains incompressible. So you do that, and you see what happens, and you do pretty much repeat that experiment now in the computer. And this is the wet sand, and you do get an instability forming for wet sand, as you can see there. I'm going to not continue this video. And for the dry sand, it's pretty stable. So what has happened in this situation is, as you can see, it's going very stably. What is the difference in this Drucker-Prager solid between the wet sand and the dry sand? The only difference, really, the main difference is the friction angle. The friction angle for wet sand is nearly 0, while the friction angle for dry sand is pretty high. It's in the 20s, it's around 20 degrees. And so what's happening really is that the friction is stabilizing the fluid. And I'm not going to go into the details of describing this problem, but let's just say it in words what has happened here. Is that you have a high pressure air interacting with this surface here. And if the yield strength, the effective yield strength of this surface is low, you get something like a Rayleigh-Taylor instability happening on this face. And that's what's happened here, is that, it's the dynamic version of the Rayleigh-Taylor instability that has happened there. And what friction has done is that because there's pressure, it has increased the yield strength of that solid locally, and it has stabilized it. And that is the reason why you get this instability in wet sand, but you don't get in dry sand, at least in this experiment. So now the question is, why is it that you got this instability on the front face, right? And you got these jets happening on the front face. And the answer is that, remember that it's really the Rayleigh-Taylor instability between when high pressure gas loads the granular medium, the surface goes unstable, basically, under dynamic loading conditions. Now, when the granular medium is moving through air very fast, it compresses the air in front of it. And because it compresses the air in front of it, the air now exerts a back pressure on it, and that's what causes that instability. And if you then simulate that, now, why is it that if you simulate it, you'll see what happens. Is that the front is now going unstable because there is air in the front here, and now you're forming that instability, and the jets start to form. So the question is, why is it that this did not happen in my lab experiment, but it happened in reality when that real explosive experiment was done? Is that you need to really move that slug really fast to be able to compress the air in front of it sufficiently to actually create sufficient pressure to cause that instability. And so you can see that, for a typical sand, which has a yield strength divided by atmospheric pressure around 0.1 and a friction coefficient of 0.1, you need to be nearly, Mach 5 really. So this is the slug speed divided by the speed of sound in air. You need to be around Mach 5, Mach 6, maybe even more to get that instability. And that is why we could not get that instability in the lab, but that is what we found. That's what happened in those experiments, explosive loading experiments. So now we sort of have understood as to how the granular medium is moving through air. The next question is, how will this granular medium interact with the structure? Because we're now coming to the problem of understanding the structure problem. So think of this. This is the granular medium. It's coming through. This is a rigid structure, and it's coming through and hitting this structure. What happens? So this sand that has come and hit this structure has already densified. And as more and more sand comes in, all that happens is that you get densification here. This sand up here knows nothing about the existence about this structure, and it's just coming here, and you get a sharp densification front. You get a shock front. This is densified material down here, and it's non-densified up here, basically. Okay, so this problem can be relatively easily understood just in the really basic mechanics. You can think of this as a simple material which has zero strength until you compress it and it reaches some kind of densification strain epsilon d, and then it locks up. And if you think of it that way, you can then understand what will be the pressure that as this thing impacts the structure, what pressure will it exert on the structure? And you can understand that by effectively just conserving momentum and mass across this shock front via these two simple momentum conservation and mass conservation equations. And you get a Rayleigh construction, which tells you that approximately the pressure that is exerted on the structure is rho v squared, where rho is the density, effective density of the sand, the smeared out density of the sand. And so it's basically telling you that it's exerting a hydrodynamic pressure on the structure to a first order, right? So now that, so this is a really very basic mechanics. So now we want to understand what happens if you have this high velocity granular medium impact in a structure. What kind of structure do we want to design? And for that, we really need to define some kind of a realistic situation. And there are two situations we'll think about. And this was some experiments by Hayden Wadley, really. So you have a structure where you explode something here and the granular medium comes and impacts it. And this is what happens, is that the granular medium just makes the structure jump upwards, as you saw basically here. And why is this interesting? Well, this is interesting because if you thought of that vehicle, you have an explosion happening underneath, and the vehicle jumps up right in the air because the momentum that has been transferred to the structure. So the question is, can we reduce the momentum that is being transferred to that vehicle? And hence, can you reduce the jumping up of the structure? So that's the one possible question. Another possible question is to ask, and you can design this kind of apparatus, and that was Hayden Wadley's apparatus. Another question that you can ask is that suppose you want to basically just have a plate, and you want to stop the failure of that plate. And this is stopping of the failure of the plate, basically, is to ask the question as to what kind of best sandwich structure could you design to stop the failure against granular impacts? Okay, so let's think about the first problem, which is this problem of jumping. And what that problem is, we are thinking of a cellular sandwich core with a face sheet and some ejecta coming and hitting the structure, this granular ejecta coming and hitting the structure. And what we are plotting here is the momentum that has been transferred to the structure. These are measurements divided by the momentum that would have been transferred to a rigid structure. And on the x-axis is being plotted the strength of this cellular medium divided by the pressure, that hydrodynamic pressure that the sand is exerting. And what you see is something interesting, is that there's an intermediate value of this non-dimensional group, which is the strength of the sandwich core divided by this pressure, at which you reduce the momentum by about 30% or something of that order. And this solid line is a prediction, which I'll explain to you in a minute, basically. So what you see is that you don't want to have a core that is a sandwich core that's too weak, You don't want to have a sandwich core that's too strong either, and we'll try to understand why that is the case, really. And of course, you can design different architectures for these different strengths, right? So an intermediate strength would be some architecture which looks like that. A stronger one would be something that looks like this. Okay, so the question is, why is it that you can understand why a high strength core really doesn't do anything, because it's going to behave like a rigid plate. It doesn't deform at all, so it's going to you're going to go to the rigid plate limit when you go to high strength. The question is, what's happening here at this low strength case and at this intermediate strength case? Why is it that the low strength is transmitting so much more? And why is it that an intermediate strength core is really being optimal? So let's understand what happens in the low strength case. This is a simulation. So this is the sandwich structure, and this is the granular medium that's coming and impacting it. And look what happens is that this core is so weak that it completely densifies, and a densification front hits the back, and you get the densification front hitting the back, and the whole structure sort of rebounds, as you saw here. Just again to show you here that there's a rebound that has occurred. And of course, we all know from simple momentum conservation that if you get an elastic collision, you transmit into the rigid wall twice the momentum of the incoming ball, right? So effectively, something like that has happened here, is that because of the rebound, you're transmitting more. Now, if you go to this optimal strength core, is it just about densifies? And because it just about densifies, it of course is like a plastic collision, and you're transmitting only the incoming momentum into the rigid structure. And that is why basically this is the so-called optimal strength, while this doesn't work. And that's what happened down here, is that in these intermediate strength cores, you basically got that intermediate strength really converted to a plastic-like collision. So the lesson we have learned here is that, of course, that once we know what strength we want, we could, in principle, backtrack what is the architecture of the core that you could want. But the lesson here that we have learned is that you don't want something that's too strong, and of course, you don't want something that's too weak either. Now, this is one conclusion, but we might reach some other conclusion if we move to another type of loading situation. So let's look at this experiment where basically you have a plate. And this is again Hayden. All experiments which have real, right? Which are real explosive are Hayden-Wadley's experiments, I should say, by the way. So you can see that this is the sort of experiment that has been done, and then you measure the deflection of this plate. And that's what Hayden did, is that he basically measured, he took a solid plate of the same mass, and he sort of measured what is the deflection as a function of standoff. Now, what do I mean by standoff is how far this explosive event was from the structure. And what that really is controlling is the amount of momentum that you transfer. Remember that the momentum scales with 1 over the radial distance square. So as you go further and further away, less and less of the explosive momentum actually reaches this structure. So as you increase the standoff, of course, you're getting smaller and smaller deflections, and that is a solid plate. These two black lines here that you've got are for the sandwich plate. And you can see that the sandwich plate is doing somewhat better than the solid plate. And those dashed lines are the front and the back plate in terms of simulations. Now, what you can see is, what do I mean by these simulations? This is the sort of simulation that we did, right? We tried to simulate that event. And what you can see is that though this looks rather fancy, it does a pretty poor job, to be honest, of capturing the experiments in this case. And at this point, we are going to move and say, there's some evidence to suggest that sandwich plates are doing better, and with appropriate cores are doing better than the solid plate. But I'm not sure, because I really don't, there are too many uncertainties with this real explosive event. And so we go back to our Cambridge lab and we say, can we do simpler experiments, much simpler experiments, where everything is well controlled? And because it is well controlled, we will be able to maybe simulate it. So what do I do in these experiments? You basically have a piston with a sand slug in here, and you come and push this piston with great velocity, which ejects out the sand slug, and then that can come and hit your structure. So that's the idea. And so this is the sort of sand slug that will come and hit this structure. And in principle, now we can simulate this entire experiment, including this impact event, the piston, and everything, basically. And when we do that, so this on the right is the experiment and the left is the simulation, it all works out remarkably well. So now, you can see that we're getting extremely good agreement between the experiments and the simulations, including if I just plot the mid-span deflection as a function of time, it all looks rather good. So this tells us that this, we've got a good simulation capability, we've got good handle over the experiments, and now we can really use these experiments to probe what is it that we want from these, in terms of design of structures that will help. So again, we are going to do baby experiments, and the aim here is not to actually say what is the core of the sandwich, but to ask the question, what properties do I need for the core? So we're going to take these types of sandwich beams. They all have simple hexagonal honeycomb cores, but interestingly, because in hexagonal honeycomb in its plastic properties, it's anisotropic, we can play lots of games. So I can change the thickness of this core. I can rotate the core in this LW plane. And when I rotate it, I keep the compressive strength in the T direction the same, but I change the shear strength in the longitudinal direction of the beam. So I can make a core that's high compressive strength and high shear strength. I can make a core by rotating it in the T plane by having a high compressive strength but a low shear strength. But then if I rotate it completely and I rotate it such that it becomes like a hexagonal honeycomb where this is the in-plane direction, the W is now the in-plane direction. You can see that I've changed the axes such that W is now in the vertical direction. Then I've got a core which has a low shear strength and a low compressive strength. So then we can try to understand what is it that we really want from these sandwiches to get the optimal performances. Okay, so then we are doing these kinds of experiments. We are impacting these sand slugs against these, or these are actually tungsten carbide granular particles against these beams. And this is the sort of deflection that we can measure. And we will then look at the deflection as a function of the sand velocity, the sand particle velocity, because remember, everything is perfectly measurable now from these experiments. And we are going to compare against monolithic beams of the same mass as these sandwich beams, and wet sands and dry sands. But now you can see that there's significant reduction in the deflection, right? I mean, factors of 5 or even more, basically, that the sandwich beams are doing significantly better than the monolithic beams. But in this plot here, I've plotted thick cores with high compressive strength and high shear strengths. And here we are showing, for example, against lots of different types of configurations of sandwiches. And so let's just focus on these thick core sandwiches, right? Everything has the same mass first, I should say, right? So it's a sort of fair comparison, same mass, same size, etc. If you use the baseline, look at this blue bar chart. If you use this as the baseline at high strength, if you then decrease the shear strength, you've increased the deflection by a factor of 2. If you then decrease the compressive strength as well, you've increased the deflection by a factor of 4. Now, if you go to a thin core and a high compressive strength and high shear strength, how do I go to a thin core? You basically just half the thickness of this core, but you make the face sheets thicker to keep the mass the same. Well, it's not doing as well as this one because this deflection is higher than in this case. So what it's the lesson you're learning from here is that from these experiments is thick cores with high compressive strengths and high shear strengths, are what you need for this kind of an application. So in this particular case, high strength is extremely good, basically. And you need thicker cores rather than thinner cores, and they will help. Though, of course, you can see here that in some cases, thick cores, if they're very badly designed, can do rather badly. Okay, so use then the simulations to really try to understand why is this the case? Why is it that high strength thick cores are optimal while for this particular application? So these are simulations now of normalized deflection as a function of this core strength, and we are showing these simulations for 2 different values of the thickness of the core. So C bar is the thickness of the core divided by the beam length. And what you can see is that as you increase the core strength for a given thickness of the core, the deflection keeps decreasing. And of course, if you increase the thickness of the core, keeping the mass same, i.e. you've thinned the faces to compensate for that, you basically again get the same trend, but the deflection of the beams is low, which is consistent with those experiments that I had just shown you on the previous slide. So the question is, why is it the case? Why is the simulations doing this? And the answer is rather simple, is that as you increase the core thickness or the core strength, you decrease the core compression. And when you decrease the core compression, you retain the bending stiffness or bending strength of the sandwich beam. This is traditional sandwich, sandwich theory, really, telling you that if you have, if you separate the face sheets by a large amount, you will increase the bending strength. And that is a very simple reason why you are basically getting this effect of a thick core and a strong core helping. Okay, so this is what we are, to give it visually to explain what has really happened is this story here, is that as you increase the core strength, you hardly compress the core, as you can see. This is a weak core, it's compressed a lot and it's lost all its bending strength, while this core strength remains very large. When if the core strength is large, you retain this separation of face sheets and you basically retain the bending strength and it performs well. And if you increase the core thickness, the same thing is that you're retained in the highest strength case, you've retained this separation, and that's giving you the good effect. Now, in these simulations, there's one more thing that has been shown here. We've shown here simulations of what I'm calling sand impact and foam impact. Now, what the hell is this foam impact? Because I've been talking about sand impact all this time. So this is the sort of impact event that we have been discussing till now, is that you have sand basically coming and hitting it. And this is the foam impact equivalent. Is that now what you can see is that a piece of metal foam is doing something extraordinarily similar to the sand, is that it's just compressing itself against the structure that it comes and hits it. And what I'm showing here is that if you basically take a metal foam of the same momentum as the sand, both via simulations and experiments, you're getting behavior that's very simple. Now, why is this important? Well, it's important because doing these sand experiments is extremely difficult, while doing these foam experiments is much simpler. So I'll proceed by basically always using these foam experiments from now on, because they're so much simpler to do rather than using the sand experiments. Okay, so we are saying to ourselves that actually these sandwich structures can do remarkably well, but I've looked only at metallic sandwich structures. The question is, can we do much better, right? Can we do much better than these metallic ones? And we go back to these Ashby plots and say, what happens if you make materials in here? What will happen, right? Till now, we've been making these kinds of metallic kinds of cores. What happens if you make architected materials sit here? In principle, we could make the so-called an octet truss with diamond. Now, that's sort of not practical, of course, but you could, and then what would happen? So, but I'm going to talk about something much more practical and say, let me make materials in here, and they're actually not that difficult to make if you give up on metals and you go to carbon fiber composites and other sorts of composites. So if you go to other sorts of composites, you start making materials here, you can make architected materials that live here. So there is some hope to do even better than there. But unfortunately, there's a catch, and let's explain this catch. So this is a honeycomb. This is a sandwich panel with some sort of a honeycomb-like, square honeycomb-like core. And if you make it out of stainless steel, these are the deflections as a function of the impulse. And these are measurements, and that's the deflection. But if you make it exactly the same mass, etc., and you make it out of carbon fiber, you're doing much better than the steel. But the catch is that carbon fibers are brittle. And because they're brittle, they fail here. So while the metals will not fail, they will just continue to go up, to much higher impulses and deflections. They're ductile. The carbon fibers fail, and that's what, so this is, for example, a simulation here, is you can see that, the carbon fibers have completely failed. They have a 1 or 2% failure strength. And nobody is going to use a structure which says, oh, I'll do better if somebody comes and hits me slowly, but I will completely collapse if I get hit hard, okay? They will never nobody will actually use such a structure. So the question is, can you make carbon fiber composites more ductile? And that's a tricky situation, because carbon fiber composites, the carbon fiber itself has 2-3% ductility at most. So how can you make carbon fibers more ductile? And again, we will try to see whether architecture can help here. So we're thinking of a composite which is 3D but it's non-woven. So you have got toes in 3 orthogonal directions, interwoven. Not, I would not even call it, it's not woven, right? These are what, just what they call in the carbon fiber literature, noobed, basically. They're just sort of interlaced in some ways in this manner here. And we do a compression test in that Z direction. So this is a compression test. We are effectively compressing these Z direction toes because these other toes are doing very little, basically. And we're plotting the compressive strength against the compressive strain. And these are 4 different experiments. And we load and we unload. And look at what strains we have reached for this specimen D, and we could have gone on much more, is we have reached compressive strains of 10% or so, and there is no sign of catastrophic failure. There is, of course, nonlinearity. This was an elastic regime, and there's some nonlinear regime that's occurring here. And then when you unload, you are basically unloading to nearly where you started off with. But there is no catastrophic failure that typically occurs in the compression of carbon fiber composites. And why is that the case? It's interesting because, so this is, we're showing micrographs now of specimen A, B, C, and D after the unloading event, right? After you've unloaded, we put it in a microscope to have a look at it, basically. So what you can see is in specimen A, there is some damage here, but not much. Specimen B, you can see these are those Z direction toes. You can see some kink bands. In specimen C, you can see more kink bands. In specimen D, you can see even more kink bands. Now, this is really interesting because if you look at it more closely, you see that this is a traditional kink band in the sense, or analyzed by Budiansky and Fleck and many others, basically, is that you can see that these fibers have kinked here, and this you're getting kinks. But in normal carbon fiber composites, you get a kink, and it sort of completely traverses the specimen, and you get an unstable failure occurring. But here, what has happened is that you're getting the kinks zigzagging. Basically, they reflect inside the toes, and you're getting a rather stable situation. So all that's happening along this curve here is that you're getting more and more kinking. And so while, of course, we have not changed the ductility of the carbon fiber itself, the overall specimen ductility has gone up more because you're consuming the tores with these kink bands rather than just getting one kink band that is going unstably across the structure, basically. So that's what's happened in this case here. Now, and this translates into shear as well, is that we get this composite is extremely ductile even under shear loading, and this is the experiment to show that it's 50% strain and it's still not undergone catastrophic failure. Although the reason for this ductility in shear is very different, is that basically you've got fibers in all directions, and so you don't get these kind of delamination failure events that occur in typical at least 2-dimensional composites. Okay, so we need new models to account for these in this case, because the strains are so large, the toes evolve in microstructure, etc. So we analyze each toe separately, discretely, I should say, in these things, and we analyze it by a crystal plasticity model with 6 slip systems in each toe, because we think of this toe basically, with these are the fibers in the toe, as you can have discrete slip systems within each toe. But there are only a limited number of available slip systems under which otherwise you'll have to get elastic deformation of the fibers. But also there's something more interesting, is that these fibers are rigid compared to the matrix. And so this is like a granular medium. And so like any other granular medium, you'd expect pressure sensitivity to be there, because effectively as these toes move, they have to sort of move apart a little bit. And so there's some kind of a local dilation effects at least happening. So this is some sort of a very straightforward crystal plasticity model with pressure dependence, of course, included in it. And if you use that, and this is Lucas Meza's work, is that when you do this compression test you can see that you start predicting these kinds of kink reflections, etc. And all the toes are discretely modeled. Similarly, if you start modeling those shear experiments, this is the black line is the experiment. This is that orange line is the crystal plasticity model with the pressure sensitivity. If you don't include the pressure sensitivity of the shear strength in the toe, then you start under predicting the experiment. And this is really important because you think this is a shear test. Why would I get pressure building up at all in these specimens? But you do get buildup of the pressure effectively because of the three-dimensional nature of that architecture and the mismatches basically between the anisotropy between each toe. So that you can see that you need the pressure dependency. You might also say, why did you do all this, complicated crystal plasticity? You could have just modeled each toe as a hill plasticity model with all the anisotropies. And if you do that, that's this line here, is that hill plasticity basically does not predict the hardening that you're getting here. And this hardening is because of the microstructure within each toe is evolving, which is being captured by that crystal plasticity. And if you did hill plasticity, you just would not capture it. So you need all this sort of complication really to capture, what are relatively simple tests really. Okay, now that we've convinced ourselves that we have, that we can make ductile composites, what happens, right? Can you do now better? So now the problem that occurs is if you want to really use these composites for those kinds of structures, you need to avoid the joint failure problem in composites. This is always a problem in composites, that you get massive joint failure. And this is a Swedish company that really helped us make such sandwich beams by a complicated, very complicated weaving process. And what they have done here is that there is no joint within the structure. So a fiber that starts at one end of the structure ends at the other end of the structure, and that's it. And you can see what's happening at the joint is that, you can see that a fiber comes this way, goes that way, and goes back that way and upwards, etc. So effectively, it's a completely integrally woven structure, much like a natural structure that when a branch comes out of a tree, there is no sort of, there's no connection here. The fibers on the branch come into the tree trunk, etc. Now, if you do that and you repeat this experiment, now with the metal foam rather than the sand projectile, this is what I'll get, is that you come and hit that composite structure and we break the metal foam. The front face has failed, the back face of that sandwich beam has not failed, but the metal foam has gone. We make an aerospace grade aluminum structure with the same mass, same topology, and everything else the same. It's extremely ductile, the aluminum structure, but it still doesn't do as well as this effectively three-dimensional composite structure, because you can see that it's just failed in this manner. Now, we are not capable at this point of modeling these kinds of experiments because we really, all the modeling that I showed you was required every toe in the structure to be modeled discretely. And we are not capable of modeling every toe in this structure discretely. There has to be some kind of homogenization that we'll have to do, but we haven't yet come to doing that. Okay, so that was problem number one. I will end, I'll go on in the next 10, 15 minutes to talk about problem two, is protection against ballistic threats. What do I mean by ballistic threat? You have some impact event happening like that. And the question is whether this thing goes, the projectile goes through or not. So if you basically take three different types of plates made out of steel, carbon fiber composites, or what I'm calling here ultra high molecular weight polyethylene composites, this ultra high molecular weight polyethylene composite seems to do remarkably well. And so, they have twice the ballistic limit of steel and maybe sometimes even more. So what are these? So, before we really try to understand what is it that we can do with these ultra high molecular weight polyethylene composites, let's try to understand what they are and why they work really. Okay, so ultra high molecular weight in polyethylene is very simple. So you take, and this is Honeywell in the US and DSM in Holland basically make such composites. And so they start with normal high weight molecular weight polyethylene and they sort of extrude it and they get some, these are patented processes. To be honest, I don't know exactly how they work. And then they can extrude it to get, very long chain, extremely high, millions in molecular weight, these fibers. And once you get these fibers, you make them into composites, which look something like this, basically. Typically 090 composites. So that's what has been, that's what these composites are. These fibers are extremely strong. They have strengths on the orders of 4 to 5 GPa sometimes. So that's why they are used basically. And so to put it in context, why is it that you are interested in polyethylene fibers rather than carbon fibers or Kevlar or something like that? it's interesting to understand why is it that these ultra-high molecular weight polyethylene composites are such good materials for ballistic resistance. And this was work done by Phil Cunniff at the Army Research Lab in Natick. And he came up with a non-dimensional group, basically, or a scaling group, basically, I should call it, which is the energy absorption per unit mass, which is this first term here, multiplied by the wave speed. And this has units of velocity cubed. And what he said is that the ballistic limit divided by this u star to the power 1/3, which will now have the units of velocity, will scale with the mass of the plate to divided by the mass of the projectile. Now, these mass and plate and projectile are structural parameters you have no control over. So if you increase this u star, you've increased the ballistic limit. Ballistic limit means the velocity at which this projectile will go through the structure. So again, we can go to an Ashby type of plot and plot this energy absorption per unit mass versus longitudinal velocity speed. And these dotted lines are contours of this parameter u star to the power 1/3. So what is that telling you is that, of course, you want to be as high up as possible in u star. And Kevlar is somewhere here, carbon fibers are somewhere here. These ultra-high molecular weight polyethylene composites are here. And of course, you can see they're doing better than Kevlar and carbon, and that is why people consider them. So let's try to understand why is it that this parameter, energy absorption per unit mass multiplied by wave speed, is there. And Phoenix and Porwal in 2003 basically gave an explanation for this. And they basically gave this explanation. I'm giving it in qualitative terms, right? That a projectile comes and hits, and a wave starts to go through. And so the amount of material that is engaged in the stopping process is proportional to how far this wave has gone, and hence the wave speed is coming in. And of course, how much it will stop depends upon how much energy can be absorbed. And hence, approximately, I'm saying that why that parameter works is that you need both high wave speed and high energy absorption to stop this. High wave speed to engage more material, and high energy absorption to basically, to absorb the energy. But now if you go and do an experiment, something doesn't seem to stack up in this case, basically. Because there is no mention of shear strength of the composite in this whole story, right? So we keep the fiber strength fixed and vary the matrix, i.e. change the shear strength of the matrix, and this is the ballistic limit. And so this is the ultra-high molecular weight polyethylene composites. As you increase the shear strength, the ballistic limit decreases. And the same thing with carbon fiber composites, that as you increase the shear strength, the ballistic limit decreases. So something is telling you that there's something wrong with that explanation. And in fact, that explanation, there's something incomplete, or in fact, I should say, rather than wrong with that explanation. So if you now do this experiment, so this is impact of that ultra-high molecular weight polyethylene composite beam with this kind of a architecture, and you do that experiment, look what's happened here, is that you're getting failure here underneath the projectile when there is no wave that has propagated, nothing that has happened, and it's just uniaxial compression-like failure. Hardly the back surface is hardly moved either. And then as you go on further, you see that this beam is shearing a lot, basically. And so, hence maybe the shearing is important as well. So really speaking, failure seems to occur by just a through thickness compressive strength and none of this complication of bending, etc. And so let's try to understand why that is the case. That why would you get failure when you compress this composite under uniaxial compression in this way? So if you do that experiment and you take a UD composite, normally these composites are 090 composites, but we don't do that. We just make a unidirectional composite and we compress it. And this is what will happen. It just compresses that way, and that's it. No failure at all. But if you now make it into a 090 composite and you compress it, something completely different happens. You get, enormous strength, look, and then it just bursts. It just completely explodes, basically, and you don't get this kind of ductile behavior that you saw here. And you get significantly higher strengths, right? This thing went up to 100 megapascals. This thing has failed at 900 megapascals. And the reason this is happening is under uniaxial UD composite, will just compress like a bunch of logs. If you press it, it'll just shear over like that, and that's how the compression occurs. But now if you make it into a 090 composite, something completely different happens. As you compress it, and these 90-degree, these other fibers, because of effectively they're bonded here, and the shear lag has developed some kind of shear strength here, is that you basically are now stretching those fibers in this way, basically. And so now you've completely changed to compress the composite, you need to push the 90-degree fibers into tension, which completely changes the deformation mode and hence the compressive strength. We can do experiments to understand all this. Of course, to get this kind of behavior, you need to build up a shear lag, and we can measure those shear lags in experiments. We put a pressure film here, and we can actually measure what is the length over which that shear lag develops, and you develop that kind of indirect tension. Because I'm going to call it indirect tension because we are compressing it, but we are putting the fibers into tension. And that's what's happening, is that compression in this direction is putting these fibers into tension because these 0-degree fibers want to expand in a Poisson manner, basically. And we can use the same kind of crystal plasticity framework for each ply that we had earlier. And we get, basically speaking, I won't dwell much into that, is the peak strength agrees relatively well with the experiments over different ply thicknesses, because the shear lag effect means ply thickness matters and specimen length. So, we think we have an understanding of the problem. Okay, so given all this, we'll return to the ballistic story. And to remind you what is the ballistic story, is that the failure is all occurring underneath the projectile, as you saw here, is that all these fibers are failing. So it's, the projectile, the failure is occurring underneath there. So why is this going to be the case? We're going to use that model and basically to try to simulate it, to try to understand this. So this is a beam, an infinitely long beam, and there's a sort of a spherical projectile that's coming and impacting this plate here like that. And when you compress it, so this is a zoom up from here, is you can see that immediately underneath the projectile here, you've developed very high stresses here. As you go further in time, these stresses just relax. And in fact, the stresses keep reducing, and then you just get this kind of a propagation of a shear hinge for a very low shear strength beam. And this is what's happening here, is that you get these very high stresses very early, which are what are breaking those fibers. And then and if they don't break there, then you're not going to get failure. And if you plot the ply stress underneath the beam as a function of the depth of the beam, you can see that really you need to model every ply discretely here, because you can see that you're going from one ply being in tension to the next ply and compression and to tension, etc. So there's this enormous inhomogeneity that has developed because of this indirect tension mechanism underneath this projectile. And then if you go to high strength beams, shear strength beams, something completely different happens. Is that you completely change the mode of deformation and you get high stresses at the back, basically, and very high stresses, and you're going to get failure at the back of the beam. And that's what happens in traditional carbon fiber composites. So to summarize this, you're going to get two failure modes. One failure mode, which occurs at relatively low shear strengths of the beams, which is occurring nothing by that kind of Cunniff mechanism, but by the development of this indirect tension. So alternate layers of tension and compression underneath the projectile, and a failure mode which will look something like this. And at high strengths, you'll get modes in which you basically develop a bending tensile strength at the back of the beam, and you get failure at the back of the beam. And then you can develop a failure mechanism map. This is the failure mechanism map after doing many simulations. And now that starts to tell you that there's something interesting in terms of the shear strength of the beam. There's an optimization here. Is if you go to very low shear strengths, your ballistic, this is sort of no failure here, and failure here, right? So you want to be in this white regime. Is that you'll do reasonably well, but as you increase the shear strength a little bit, you maximize where this ballistic limit, would be the ballistic limit, because you're going to get at this shear strength, you're going to get failure at that point at say 250 meters per second. But if you increase the shear strength any further, you hit this mode 2, which is this bending failure mode, and it reduces the ballistic limit very substantially, and you're now going to get poor failure. So it's very interesting. It's telling you that it's not sufficient to have high fiber strength, but you need an intermediate shear strength really to actually get the optimum ballistic performance in this case. So what has that told us about how to actually improve architecture to improve ballistic performance in these kinds of composites? So one obvious thing is you say, of course, if you increase the fiber strength, you're going to help. But in some ways, you reach the limit to that. You can't do much. So the question is, can you change microstructure? So we are starting with fibers like this, and that's what we've been doing. But suppose we don't do fibers and you go to tapes and you don't make these kinds of composites with microstructures that look like that, but tapes that look like that. Now, the reason we were getting failure by that indirect tension mechanism is this Poisson effect, where effectively these layers of the composite were trying to expand by a Poisson effect and were putting these into tension. If you reduce this Poisson effect, then you're going to reduce the amount of tension generated in these layers here like this. And that's what the tape-based composites are hopefully going to do for us. And that's what we are trying to do right now, is that this is now a tape composite. Its current tape composites have a lower tensile strength compared to the fiber-based composites. But when we do a uniaxial compression experiment, which is really what's happening underneath the projectile, as we have seen, the tape composites are far better than the fiber composites at the, for the same kinds of even though their strengths are low. So we are hoping that the tape-based composites will be better than fiber-based composites, and especially if you get the tape-based composites to be the same strength as the fiber-based composites in the tensile strength. And this is a sort of a simulation map which is showing what will happen if you make a tape-based composite. So the dotted line is showing the mechanism map for a fiber-based composite. This is the tape-based composite. So it's telling you that not only will you increase the ballistic limit if you go from fibers to tapes, but you'll also increase the shear strength at which the optimum performance is reached. And this is important to increase the shear strength, because in principle, if you have a high shear strength, then you can start thinking of this as a structure, because right now these composites with 5 and 2 megapascal shear strengths are not structures. They are sort of parasitic when you use them. So hopefully what I've told you from all of this is the following, is that architecture helps, and it's not always good to be saying that strong is needed for all kinds of applications, but you really need to understand what is the mechanisms at play. And if you understand those mechanisms at play, you may understand what happens, how to best design a material. And I see that I'm sort of running a bit late. So the main thing which I will say is that you first need to understand the mechanisms. And those mechanisms can tell you to improve architecture. Sometimes it may tell you that you don't need high strength. Sometimes it may tell you need extreme anisotropy, but sometimes it will tell you need extreme strength, like for the bending of beams impacted by high velocity granular medium. But in nearly all cases, it will vector the development of new materials once you understand the mechanisms at play. Thank you very much.
Thank you, Vikram. Yeah, now can we ask you to unshare your screen so that we can start the discussion and Q&A? Yeah, for all the audience, if you have a question, please press the hand raise button so that I will create a list. Then you will be called following the list. Yeah, let's start with Jiangsu Kim. Please also introduce yourself. We need to promote Jiangsu to the panelist. Yeah, thank you, Vikram. That's very inspiring talk.
Thank you. I'm not sure.
Hello, thank you so much. Thank you so much for the talk. I could learn a lot about the projectiles and highly impact resistant materials. I have two questions on ultra high molecular weight fabrics. One is kind of recap. So strength was related to the mode of the failure. Why the strength or why low strength can avoid the bending failure at the bottom of the film? That is one question. And the other question is, this is more kind of comments. So I saw your idea on packing a rod array into the rectangular array. Maybe because the polyethylene has a very low melting point and glass junction point, maybe we can compress with a lot of heat to remove all the voids between the cylinder rods. Maybe it can help to improve their impact resistance. Thank you so much.
Thank you for your question. So I'll answer the second comment first. Is in some ways that's exactly what DSM are doing in making tapes, is that they start with fibers and then they compress those fibers at high temperature and change the topology basically of those fibers. So that is precisely your idea, is what they are doing, and maybe they have patented it as well. So I don't. Your first question regarding the shear strength. So the thing is that if you have a high shear strength beam, i.e. this is like an Euler-Bernoulli beam, then of course all that you get is you get a compressive stress at the top and a tensile stress at the bottom, and that's all that happens. But now you think of taking the limit of a Timoshenko beam, i.e. a zero shear strength beam, which is like a telephone directory, and I can bend the telephone directory and I can deflect it, but it doesn't really bend, it's just shearing, and I'm not developing any stresses at all in the fibers. And that is why the low shear strength of these beams is actually reducing stresses that are being transmitted in the fibers, and a completely different failure mode is coming into play, which is that indirect tension failure mode.
Thank you. Thank you.
Next, Tan.
Hi, Lihua, it's me.
Yeah, we can hear you.
Okay, yeah, thank you. Hi, Vikram. So thank you for a very nice talk. And I have one question about your material. Like now people also design many material structure with negative boson ratio. So how do you think that if you design the architecture material with negative boson ratio, how that will influence or change your impact resistance?
So this is for the ballistic app. Just to clarify, you're thinking about this for a ballistic kind of application.
Yes, yes, yeah.
So the honest answer is I don't know. The only thing which I will say is that most negative Poisson ratio materials that I know of are cellular materials, i.e. they're voided materials, basically. They have a lot of voids in them. And that, usually speaking, is very bad for ballistic resistance, because the thing will just goes through us. The material is too soft in that respect. There's the compressive failure mode that you get in a sort of a compressible medium, basically. And so ideally I'm not sure that you can get away by using those kind. Now, if you tell me that you've come up with a negative Poisson ratio material that is effectively a fully dense negative Poisson ratio material by using 2 or 3 phases, basically, that's a different story.
Yeah, I have a colleague is doing this kind of study for the fiber reinforced composite. So he can design this fiber orientation and multi-layer to achieve negative boson ratio. So it's a fully solid material. I'm not sure if that will help.
I'm not sure negative is needed, but 0 will help enormously. I mean, this is what the idea about the tape composites was, that you go to a 0 Poisson ratio material. So without any question, 0 will help. Now, I don't know whether negative is needed, but if you can make 0, there's no question that it will help.
Okay, thank you. Yeah.
Next, Stavros.
All right, thank you so much. That was a great talk, Stavros Granulas from Johns Hopkins. I had a couple of questions. It was very interesting when you did the same experiment for the sand and the foam, and you showed some similar quantitative results, right? When you do the two plots, and that was, well, my question first was, I expect that the impact velocity must be pretty high because I think the shock was in the shock regime, the foam. So I expect it was more than 80 meters per second, right?
Yes, you have to be in the hydrodynamic or what you're calling the shock regime, basically.
All right, I expected that. Now, the question is, did you get that by, well, not by accident, but when you say, oh, I use the metal foam, but the metal foams, you can use an open or a closed cell foam or different densities, and those are going to have different strengths. When you get that match between the sand experiment and the foam experiment, did you do some type of prediction before you did the experiment? You thought, okay, what strengths do I need of the foam to try to get that match of the experiment? Because I'm pretty sure you did something like that, right?
Sorry, so I'll now need to explain that thing a bit more clearly. So I'm in a regime where rho v square is much bigger than the strength of the foam. So you can forget about the strength of the foam, okay, because the hydrodynamic regime. So now I've shown by the very simple Rayleigh construction that the pressure that the foam or the sand will exert on the structure is rho v square divided by the densification strength. So I design a foam that has going to give me the same hydrodynamic pressure as the sand impact, basically. That's step number one. And step number two is we need to get not only the hydrodynamic pressure correct, but the total momentum the same as well. And that means I need to change the length of the foam such that the total momentum of the foam is the same as the total momentum. So actually there's a one-to-one correlation between the sand experiments and the foam experiments, basically.
I see, okay, that was the trick. All right, and now a very quick question in the beginning when you showed about the core strength and you were trying to, I guess, minimize the momentum transferred, and you showed that there is an optimal value of the core of the sandwich that is not the highest, that gives you the lowest transfer momentum. But then in those experiments with the plate, you showed that, the honeycomb out of plane, which is kind of the best option. But there you're trying to minimize deflection.
Correct.
So it's kind of two different types of
yes. Now you're going to ask, yes. So, I mean, that is unfortunately the truth is that, if you have two different types of situations, you're going to have these two different contrasting requirements. And I'm not trying to say what a real designer will have to do, because that will depend very specifically on the details of the design. But what I'm saying is that if you want to reduce momentum transfer, you'll have to reduce the strength of the core a little bit. And if you want to reduce, but quite often, if these structures, at least in some cases, are really rigid, and all that they're interested is in minimizing the momentum transfer and nothing else really.
All right, thank you so much.
Next, Robin. Yeah, everybody, please introduce yourself.
Hi, Professor Deshpande. Thank you very much. That was a wonderful talk. I learned a lot. I actually missed your Gaussian talk at Caltech for that one. So I'm working with Kaushik Bhattacharya at Caltech now. I will be moving back to Boston at Northeastern as an assistant professor. So Brigadir is my colleague now. So I have two questions. One is, this has puzzled me a lot about figures of merit on energy absorption. Now you have the something like specific energy absorbed, but that could be one figure of merit. I think people talk about that, but the other one, I think maybe when you try to absorb something, then there's momentum transfer, and maybe more important, the force, which means, for instance, when I try to design the material, perhaps I want some viscoelastic or time-dependent behavior such that over some longer time, I have a smaller force. I feel just by the human body, for example. So the question is, how do we talk about this? And what about the figure of merit here for this problem?
In some ways, I think what I was trying to tell you, maybe I was not clear on, is that these figures of merit are useful. Like the Cunniff figure of merit is very useful, but it has its limitations, really. And this is what I said, is that it had missed certain very important physics. But it doesn't mean that I will criticize it, because I still think it's a good first order way to think about the problem, really. So you're absolutely correct that in dynamic loading applications, spreading the momentum in space and time, basically, is extremely important. And that is why sandwich structures in some ways work, right? Because you're spreading the momentum if the minute you spread it in time, you reduce the same momentum, you reduce the pressure or the force. And similarly, if you spread it in space, then you have increased the amount of area over which the energy absorption is happening, which is what Cunniff had appreciated, I could say, right? By bringing wave speed into the game. He was recognizing that the wave speed is helping you spread the momentum over the impact over a larger area and engage more of the material, basically. So I'm not, I don't think that you can completely dismiss figures of merit, but you have to do a detailed analysis. There's no question about that.
So just follow up. Even with that, when you show that dimensional analysis, we're still talking about there's some energy form that the you mentioned. So do you think, of course, this is a design problem, then people need some, as you said, it's not complete, but people may need some parameters to design just to optimize. Do you think there's other parameters that's important? For instance, even you have a wave speed, then it's still goes into the energy. The question is, do you think there's additional necessary parameters that need to be designed?
I think so, Mia. That's what I was, for example, I gave that deformation or failure mechanism map for that impact loading, where shear strength was an additional parameter. Actually speaking, that was for one ply thickness. Ply thickness becomes another, you can do another, it's about, I could have shown a series of maps with lots of changes of the design parameters, basically. And unfortunately, there is no simple answer. Hence those Ashby plots, failure mechanism maps are so useful. At least if up to 3 dimensions, you can visualize it. Beyond that, it's tricky, really.
Okay, thank you. I will shut up. Thank you.
Yeah, I have actually a very related question. Yeah, because now for architecting material, you really have a wide design space. How can we apply the lesson we learn from one material to another? Or can we design a gradient structure or some heterogeneous structure so that you learn the lesson, then you know how to optimize the design? Or
so what I was trying to say, Leo, in this talk was, as a first step, without going into the detailed design, at least answer the question, what effective properties you need, basically. When I was talking about core strength, shear strength, or things like that, I was not saying anything about architecture. I was just saying, let me understand what effective properties do I want. And I think that is step number 1. And after that, of course, there will be further design iterations. Then once you actually design a particular architecture, then to understand what will be the precise failure modes that will occur. But in many ways, sometimes people just assume a priori that they know that what effective properties they need, basically.
Okay, next, Kejie.
Thanks, Lihua. Yeah, thanks, Vikram, for very nice talk. I'm Kejie Zhao. I'm a faculty at Purdue University. So good morning from West Lafayette to everyone. I have a couple of questions on the carbon fiber composite. So you showed this ductility achieved by architecture design, and this ductility by, if I understand correctly, by the shear kinking and the reflection. And you also mentioned this carbon fiber is brittle. So I'm wondering, how does carbon fiber behave plastically in that composite? So this is first question. I might misunderstand your the kinking and the reflection mechanism. And second is that you mentioned that there's no catastrophic failure upon the first compression. And we also see a significant hysteresis in the first cycle. How about the second cycle and the following cycles for that structure?
Okay, so I'll answer that second question. The second question about cyclic behavior, I don't know is the answer because we haven't yet done such experiments. But I will say, let me answer your question about the ductility. So there is no question that within each kink band, there is 2% strain. There, that is, the carbon fiber cannot take more than 2% strain within each fiber locally, basically. But the only reason you're getting macroscopic ductility is that unlike in a normal carbon fiber composite where you get one kink band and it just crisscrosses the entire specimen, here you're getting reflection. So if you're getting 2% in every kink band, then overall, you're going to get a much larger ductility, basically. But it's the difference between getting failure by shear banding versus homogeneous failure, basically.
Right. Yes. So then maybe a little more is how that reflection happens, why the shear kinking is reflected. Yeah.
So Lucas, of course, will tell you a lot about this because that was his work. But he can butt in at any time. But the reason that you get reflection is that in a three-dimensional composite, what's happening is that you get kink across one toe, then it comes into, it basically hits another toe where the fibers are in a very different direction where they can't kink, basically. And so it has no choice but I'm saying it qualitatively, but it has no choice but now to reflect back into the current toe. While if you had a two-dimensional composite, standard laminate, it had an entire band basically that could go through.
Okay.
Now, you can make other composites, right? Three-dimensional woven composites will do something similar, but they have so much waviness, fiber toe waviness in them, is that they get, you've had an effect on their compressive strength as well as stiffness. While here, the toes were straight, and that's the difference, really.
Yeah, that's very interesting. I might miss that part. So you showed this model and this different slipping system for a system so that which can capture this plastic deformation behavior. Were there experimental for this kinking and reflection experimental image about that? I might have missed that part.
Yeah, I did show, I think, the reflected kink images, experimental images, basically.
Okay. Yes.
In fact, there are such, the kinks were far more defined in the experiments than they ever were in the simulations.
Great. Thank you very much.
Next, Li Qing.
Hi, thank you. Thank you very much for giving us this very interesting talk. I'm Li Qing from Institute of Physics of Global in Paris, in France. I'm in Europe, the same time zone. So yeah, your talk is very interesting. I have a kind of technique, a kind of a specific question on the failure mechanism map of your impacting experiment. So you showed the model 1 and the model 2. So you use the tension strength of, I don't know what kind of material. It's the tension strength of the fabric or the tension strength of the entire material, this complex material to identify what kind of situation you can get crack inside the fabric structure, or what kind of situation to get the crack outside of the this structure. So this is one question. Another question is, you just test the shear strength, or what about the tension strength, and what about the entire strength of the material? That's, do they also affect? Yeah, thank you very much.
So I should clarify a few things. Is that the failure criteria is based upon the tensile failure strength of a given ply. So you take a given ply with only fibers in one direction, and you do a tension experiment along the fiber direction of that ply, because it's a unidirectional ply. And that is defined by tensile failure strength used in the model. And so effectively, there are approximately two parameters that are defining a ply. One is the tensile failure strength of the ply, and the other is the shear strength of the ply, basically. And so those are the two parameters that govern that map that I showed you. So it's not the tensile failure strength of the whole composite, but of each individual ply.
Yes, yes. So then you also identify the strengths, the shear strengths could, divide the group of failure into model 1 and model 2, right?
Sorry, can you repeat your question?
You just observe the only one parameter, which is shear strength, could, make us a lot.
So if you fix the fibers, see the tensile strength of a ply is basically set by the fiber strength. So if you fix the fibers, then it's only the shear strength, which is sort of a function of the matrix that basically governs the properties of that composite.
Okay, I see, got it. Yeah, thank you.
Next, Mohammed.
Thank you very much, Professor. I got so fascinated by the talk. So my name is Mohammed Torki, and I've been working for more than a year and a half with Professor Deshpande as a postdoctoral associate at Cambridge. So got a couple of questions. First thing about the failure towards the back of the specimen. So I'm motivated by the fact that one of my former colleagues at A&M has been simulating some analyses and some on deformable anvils, and his performing some large deformation analyses. And what he has observed towards the back of the specimen is some sort of shear bands. And of course, this happens because of an induced sort of anisotropy within the fibers. So I was wondering if you have ever observed or probably anticipated any sort of those instability type failures towards the back of the specimen. And another question that I had was quite genuine about your sort of approach. That is, so have you ever thought, or are you ever planning to think of microstructural parameters in terms of measurable or observable microstructural parameters such as porosity, and if in the effect it induces on the overall ductility and of these of these multiplied of these of the overall material basically.
Okay, so Mohammed, thank you. So first question about what happens on the rear face. To be honest, we've done lots of experiments, and to the best of my recollection, we've never observed an instability prior to tensile fracture on the rear face. But I'm not sure why we would that is the case, but that is what I'm just telling you across a whole range of material systems.
So I would probably because the anisotropies are not activated. So if you could activate those.
So these are extremely anisotropic composites. So for example, the ultra high molecular weight polyethylene composites have a tensile strength of about 5.4 GPa and a shear strength of 2 or 3 MPa. So these are extreme anisotropic. But I have not observed it. But that is, it could be that we have not been looking correctly, right? I can't be sure about that. Now, with regards to the voids in the matrix, there is no question that the shear strength that I quote is a shear strength of the ply. Now, what is governing that shear strength is a complex interaction between the bonding.
All right, Vikram, we lost you. So we can do machine learning to extrapolate.
Yeah. I'm sorry, Professor. You just got disconnected. So could you recap your last answer? Yeah.
You can hear me now, right?
Yes.
Okay. So the machine is that what the effect of the voids and the matrix and the bonding between the matrix and the fibers has on the shear strength, I have not looked at, but there's a whole ranges of literature, I mean, very large literature in carbon fiber composites, specifically looking at that issue, basically.
So you've just taken it for granted for frozen sort of microstructure.
So this is, my whole talk has been on saying that if I have an effective shear strength, then what will happen? How that effective shear strength comes about, I have not said, basically. And I've said that's a separate design issue as to now, if once we know what is the shear strength we want, how do I design the correct microstructure to give me that effective shear strength?
Yeah, thanks a lot.
Next, Brian Cox.
Good evening, Vikram.
Good evening, Brian.
Lovely talk as always. And since I start listening at 6:30 in the morning, I'm very grateful to you for being so clear.
6:30 in the morning, Brian.
Yeah, I blame Zhigang. So anyway, I'm Brian Cox. I live in California. I have a couple of sort of far out questions, Vikram, if you don't mind. Regarding essentially dream-like material properties that you might aspire to achieve certain functionality which isn't present in the current technology, which I think you've probably surveyed pretty well this morning. So first, whenever we load a plate ballistically, some part of the structure goes into tension.
Yeah.
And of course, the high molecular weight materials with very low density and very high strength are very seductive. They give you great stiffness and strength. One thing they don't do, though, is behave, if you like a cold drawing material. So think of a material that undergoes significant damage, so some strain, that reaches some strain and then becomes stronger.
Yeah.
And when that happens, the classical experiments, you get a piece of Ziploc bag, for example, and start pulling it in tension, and it will go from an initial length of 6 inches to a length of 6 feet or whatever. That would appear to give the possibility of spreading the damage away from the damaged site, which in some of the things you showed late in your lecture doesn't happen. So you end up relying just on the shear properties of the sandwich foam, and the skins have essentially gone out of the problem because they've failed. So there's one instance of a material property that might be desirable. The second thing is this. Your ballistic structure can quite often get hit more than once. And of course, just about everything that anybody has done successfully so far sacrifices the material to absorb the ballistic impact.
Yes.
So then the really far out question that I have, that I'd like to see what you have in your mind about, is this. Is it possible to imagine some combination of, well, maybe two things? One is fluid-like absorption of energy rather than material failure absorption of energy, or if you like, absorption of energy in frictional processes. And some kind of active material that would be able to restore itself after very large nonlinear deformation so that it could present itself to the next ballistic event looking pretty much the way it did before it got hit the first time. I'll stop.
So Brian, I'm not sure I'll be able to answer any of your questions, but I will try to answer some of them at least, okay? So I will say about fluid-like behavior, I will say that in fact, the ultra-high molecular weight polyethylene composites are precisely fluids. They have a shear strength of 2 megapascals and a tensile strength of, few GPa. I mean, that is damn close to a fluid is what I would say, basically. So in fact, that's precisely what they're doing, is that they are behaving as these kinds of frictional materials which are sort of, effectively spreading out the impacting energy by a fluid-like mechanism. The multi-hit problem that you're referring to is absolutely critical, right? Nobody is coming and hitting you with one bullet. They will always hit you with multiple bullets in quick succession, basically. And in effect, what I will say is the following, is that what you have to design unless you go to some kind of active process, which is very difficult because you need to restore back in microseconds, right? Because the next projectile is coming a few microseconds after the first one, really. Is if you ignore these kinds of active events and you want to basically go back to our usual passive story, effectively what you need is you need to have such a high ballistic limit that the first impact has done nothing to you, basically. That is approximately the aim that you're designing at the moment, really. So every bullet is hitting a near undamaged structure, really. And that is not great because that is completely over designing these materials, basically. But that's where we are. And I'm not sure I have a better idea, Brian, to be honest, about how do you get hold of, you can start thinking of layered composites, you can think of lots of other things. But if you had the capacity to have infinite weight into your structure, then sure, you can do anything. The game that you're playing with a moving vehicle or a body armor or anything is that you're trying to limit the weight of the structure, basically. The third thing which you have raised, which is about a hardening structure. And this is, Liu was trying to ask me this, but I sort of ignored it when she asked me this. But this is the game in sort of architected cores for sandwiches. Is really speaking is if you really now want to go into deep design of it, you'll design a graded core where initially you're soft, so you basically transmit less momentum, but then you become harder and harder as you go, you compress more and more so that you don't lose that bending effect. So you can now start grading the structures to trying to get some more complex behaviors, which is like your hardening behavior that you were talking about. Is that you can play such games. The problem with all of this, we've done some of this, is this starts becoming really specific to an application, really, rather than making general design rules, basically.
Thank you.
About reusable energy absorbing material, yeah, I just send a link in the chat. We developed a recent granular metamaterials and try to harness the energy absorption, but you can reuse it. Yeah, but it turns out the energy absorbing capability is still way lower than those plastic materials. But we try to develop more. Okay, next, Lucas.
Hey, Vikram. Really nice talk. I'm glad I was able to wake up for it. It's still 6:30 over here in Washington too. Yeah. So I'm Lucas Massa. I'm an assistant professor at the University of Washington, and I recognize some of the work in there. So I was curious what if you'd done any work. So I guess the next level of complexity over a 090 or maybe even like some composite layup is adding a third direction fiber. And I'm wondering if you've looked at or thought about adding that third direction, maybe like a steep woven architecture, because we did see that in the interest of creating a strain hardening material, we did see a 3D architecture gave you that shear hardening. Obviously, then you would take a hit in the tension, in the tensile strength, because you're then moving the fibers out of the plane. So I don't know if you've done that or if you have any maybe intuition or insight into that.
So what has been done, and this has been done by people who have worked with us and then gone on, to Karthik, Ben Russell, some other people have done this. They have looked at coming up with optimal architectures where in plane, not out of plane as you're saying, but by instead of 090 having 090, 60, whatever, right? Things like that, basically. So first question I will say is that that has a significant detriment over the 090 behavior. Now, the question which you are talking about is basically created a woven ultra high molecular weight. I'm going to call it a woven one, basically. We've just started work on that. And the reason we have only started work on that is that to weave an ultra high molecular weight polyethylene composite is very difficult, right? This composite, these fibers have nearly zero van der Waals bondings, right? So they're very slippery. They don't stick to anything. To weave something which has zero friction is extremely difficult, basically. And so DSM have just about come up with some techniques to, to do something to these fibers to allow them to become weavable, basically. And so that's precisely where we are going now. Whether that would be useful or not, I don't know, Lucas.
Okay. Interested to see where it goes.
Next is supposed to be John Sebastian, but John mentioned his question has already been answered, unless, John, you have anything else?
So my question was already answered, but I was also wondering, Professor Vikram, about the temporal discretization in the way you handle ballistics. So how do we discretize on the time scale? Does that kind of make sense? So
you mean
what is the time? So
you mean to say the numerical method in temporal discretization, or are you talking about something else? Maybe I've missed it.
No, I'm just wondering if both with the numerical approach or with in the experiment, in the actual experiment, the way we spread the impact over time actually changes the dynamics by a lot. So, how do you handle that step or that field? What is the approach?
Maybe I've not, maybe I've not fully understood your question, John. But I mean, in some ways, the numerics is really straightforward, right? Because this is an explicit dynamical simulation. The time period of this whole simulation is in a few milliseconds, which is ideally suited. So there is no temporal there is no sort of temporal homogenization that I need to do in any significant way at all. If you're talking about the physical issue about how we spread, how would you design a structure to spread the deformation as much as possible? Kanif's idea was to do it through wave speed. I will say the correct way to do it is basically to do this fluid idea, is to basically to not, that early impact, because it just shears and you don't build up any stress at all until you get large deformations. That is the way to do the spreading, basically.
I think I formed some mental image, but I'm not sure if it's the same one. Thank you, Professor Vikram.
I'm not sure I answered your question, by the way.
I think I can imagine something, but yeah, I'll read up a bit on it too. Thank you.
Next, Daniel Rattel.
Hi, Vikram. I really enjoyed your talk. I learned a lot from that. And I'm Daniel Rattel from the Technion Israel Institute of Technology. So I will just ask short questions because I guess you must be exhausted. The first remark I wanted to make was about the second or third impact, but Brian Cox. Hi, Brian. Brian alluded to that. So one of the things that maybe I missed is the issue of damage after the first hit, and whether did you assess if there is any permanent residual deflection, change of residual strength, micro CT experiments, metallographic sections, or anything that would assess damage, because that would tell you something about the capability to withstand a second impact. Or I might ask the question differently: is a good performance in terms of deflection after one impact, is that your guarantee that the structure or the material will perform in a superior way throughout its life?
So you're absolutely correct. We have done a lot of, not only post-impact CT, but we have done also post-impact strength and stiffness measurements as a gauge to which, I didn't have time to present all that.
Okay.
Now, what I will say is that those 3D woven composites, carbon fiber 3D woven composites, are absolutely the best in terms of post-impact performance. These ultra-high molecular weight composites, in some ways, are not very good at all. Though they give extremely good initial impact resistance, they're terrible at what you could call post-impact properties, basically. And so you've absolutely hit the right point, is that, what is it that you're trying to optimize will change the conclusion as to what is it that you really want from your structures.
That's really mind-boggling. Thank you very much. So I can go to the next provocation. I noticed that throughout your report, none of the targets got perforated. Would you mind to comment about that?
Sorry, in which, sorry?
And none of the targets got actually perforated.
Oh,
so,
no,
no penetration. So would you mind to comment about that?
No, so in the impact simulation, in the experiments, there, we absolutely went to complete perforation, basically.
Oh, okay.
But in the simulations that I showed, I was showing only to the first failure event. And then I will tell you why that is the case. We've done post first failure events, but there is a completely separate issue of mechanics to be discussing about how to actually model damage propagation under dynamic loading.
Yeah, absolutely.
In a consistent manner, because this issue with regards to what I would call, if you wanted to say loss of ellipticity, mesh sensitivity, whatever word you wanted to call it, is so serious in these dynamic simulations that I find it's really hard to trust what I would call the damage evolution simulations. So most papers that we publish, we basically go only to first failure. For this reason is that I'm not, and that's a completely separate story to be discussing.
That makes sense. But if I may, just a short remark, would you say that the deflection performance is a good guarantee regarding penetration? Or do you see a correlation between the deflection and the penetration resistance, or are these two completely separate features?
In fact, they could be inversely correlated.
Thank you. Thank you very much. I really enjoyed it. Thank you. And
next, Matthew.
Hi, Vikram. Very nice talk, really. I am Matteo Ciccotti from ESPCI in Paris, and I can also tell you I learned many things in this talk. Thank you. I was very curious in something you showed at the very beginning about explaining these jets by the Rayleigh-Taylor instability, and I'd just like to ask you how much this allowed to predict the number of jets, or does it give you at present any quantitative connection with the wavelengths which are predicted by this? Okay. What does this depend on?
Okay, so you can do the Rayleigh-Taylor analysis, and what it will tell you, because it's it's the first perturbation basically, is it will tell you the first the first bifurcation. It's not really a bifurcation; it's the first growth of instability. So it'll tell you that at the first instant, what will be the the number of jets that will form. Unfortunately, what it will not tell you, and I have not, I don't know anybody who's done this accurately, which will tell you how these instabilities evolve, properly, basically. And the reason why that is really hard is, and this is like the post-bifurcation problem in solid mechanics, is the reason why it's hard in this problem is that as you form the jet, you basically reduce the density of the granular medium more and more. And so this constitutive description that I have of using the granular medium as a Drucker-Prager solid becomes more and more silly, basically. The Drucker-Prager description is only valid while the granular medium is in an extremely dense state. As the density of that granular medium decreases, as it spreads, the Drucker-Prager, and so you need to have a constitutive description of some sort which you believe, basically. And so none of our simulations, whether numerical or our simple analytical kind of perturbation simulations, actually succeed in capturing those number of jets, basically. And this would be a wonderful mechanics problem because forget this explosions. I mean, for volcanoes and lots of other applications, people want to understand this problem.
Yeah. Then, okay. So maybe the link with the initial bifurcation is difficult, but can we get any information when we look at the number of jets with something which tell us how was the explosion? Like, does it depend more experimentally, let's say, on the size of the initial object, or on the energy of the explosion, or on the speed of the, what can we learn when we look at this kind of images?
For a given granular medium, you can then learn, you can get scaling relationships like this. But really speaking, the number of jets is very strongly dependent, at least in our simple models, on the so-called friction angle, basically. And so it tells you a lot more about the constitutive description rather than about the explosion as such, I would say.
Okay. Thank you a lot.
Next, I believe Jiangsu has another question.
Thank you. And I also forgot to introduce myself. My name is Junsu. I am fourth-year graduate student of Professor Jigangsu's group. And I have one more question. It's about composite. So I see so many composites that are superior to the impact resistance. For example, in the case of the aircraft, we make a composite with carbon fiber with some polymers. So they are different in many ways. One is stronger and one is less stronger than others. And somehow they are, they form a composite. So in the case of the carbon fibers or high molecular weight polyethylene, and if I can add one more material as a adhesive of the fibers, which materials should I choose to improve the impact resistance?
So not, I don't know the answer to that in that respect. You're saying in what kind of hybrid to make, basically, to improve the impact resistance. And I think we can come back to a question that we've asked before. There's no question that if on the front surface you put some kind of a viscoelastic, viscous kind of soft material thing, which will do the spreading of the load, that will certainly help in the impact resistance. Now, whether that is a practical solution and whether anybody would want to do that in a real engineering structure to put some kind of a soft coating, I don't know, basically. But I will say, I will answer the question. I will not answer the question, but I'll pose a different sort of question to you. The real issue is not at this point impact resistance. Let's talk of an aircraft, okay? Is that where do you use impact resistance in an aircraft? You basically take your jet engine and you put some kind of a casing to catch the impact. There is the blade off, that if the blade comes off the engine and it flies, you don't want it to go and penetrate the fuselage, basically. So you put some kind of a ballistic, fabric or something like that around your jet engine. The problem with that is that you use polyethylene for that. You will basically use it as a parasitic material. It is serving no purpose other than it's the ballistic resistance. And weight is a serious problem. So I will say it the other way. If you can basically use a material that will serve not only as a ballistic material, but also give you structural load carrying capacity, then you have done something good. And for that, I will say that you need to weave carbon fiber into your polyethylene to give you both some structural performance as well as ballistic performance. So I will say that, Tony Evans used to love using this word called multifunctionality. And this is not what modern people would call multifunctionality, but it's sort of a multifunctionality, is that you not have parasitic structures, to have structures that, that you want to have a structure, but it can also serve as a ballistic thing. Jacket. Right?
Thank you. Thank you.
Next.
Sorry.
Zhigang, we lost Zhigang.
Oh, yeah. Oh, sorry. I didn't hear it. Okay. Wonderful talk. Vikram, you have made impact the most interesting thing this morning.
I'm not sure.
Yeah, hopefully tomorrow and next month, next year. If I just know so little about the impact, I have a few elementary questions. So I often heard people, especially car people, talk about a crash worthiness.
Yes.
What do they mean about that word? What kind of experiment they do?
Okay, so Jiang, in crash worthiness, let me just, so let's say you have a car that is traveling at 30 miles per hour and it impacts. So you know the amount of energy that you need to absorb to stop this car, because you know the kinetic energy of this car. So that is one metric, but that is not what you would call crash worthiness, because you can design lots of materials that will absorb that much energy or structures. But you need to protect the passengers inside the car. That means you need to absorb that energy at a given stress level or a given force level, not exceeding that force. So in crash worthiness, they will look at the combination of energy absorption, but at what stress level.
Yeah. Okay. Thank you. Thank you. Also, so people also talk about using rubber as an energy absorber.
Yeah.
So what's the difference between, I can think about simple difference between rubber and a plastically deformable material as energy absorption material. So what's your take?
So, rubber, if you have high hysteresis in the rubber, then I will say that it is an energy absorbing material, basically.
Yeah. Yeah.
And you like to use it because it is recoverable, as Liu was basically saying, that you can design an energy absorbing material that is recoverable. It's fantastic, basically. But unfortunately, most rubbers, the amount of hysteresis that you get is not the same as what you get in these completely plastic materials, basically. And so you don't get enough energy absorption. But now let me just give you another example, which is sort of interesting. I didn't speak about that at all. Is if you ask the question on lots of these missiles and NASA rockets, they use elastomeric foams as energy absorbing materials to stop vibration. And so the question to ask is, where is so much energy absorption coming from a material that's made from a complete elastomer, basically? And the interesting thing is that they have done architectures which basically result in internal vibrational modes, basically, of an elastomeric form at a macro scale, not at the not at an atomic scale, basically, which gives you energy absorption, because effectively you have locked up the energy in internal vibratory modes. So you can end up with elastomers also with proper architecture working as energy absorbers, basically, in some sense, basically.
So we're also students are learning about a high molecular weight polyethylene fastening materials. A few simple questions for you. We don't know the answer. So the matrix, what is a matrix typically, and how do people ensure adhesion between that matrix and the polyethylene?
Huge problem and very good question. So the current matrices are either polyurethane matrices or polyethylene matrices. But remember that this is not only a high molecular weight, but the crystallinity of these fibers is around 95, 99%, basically. So the only bonding that you get between the fibers and the matrix is effectively van der Waals bondings and nothing else. And so the bonding is extremely poor, basically. And so you get very poor bonding. And effectively, in some ways, for these ballistic materials, that's working in your favor, because you want low shear strength, as we have just discussed, basically. And so this poor bonding is actually helping you. I mean, that's not what they were designing them for, but that has actually helped them inadvertently. Now, this is the problem that's occurring when you move to suppose I say to you that now I want to make a structural composite. You need shear strength for a structural composite. And that's where these materials fail. And so they're trying to now interweave a little bit of carbon. This is what I was trying to say in the previous question, really, is so that you can then get some bonding between the carbon fibers and the matrices to give you some shear strength, basically.
Yeah, thank you. So I was reading about these fibers, polyethylene fibers. They say they have to show photos. When you bend the structure, because intermolecular chain interaction is very weak, van der Waals interaction. You easily cause a fiber kinking.
Correct, that's right.
Does that cause problem in impact
So it's
experiment?
interesting. So it's really interesting. So, you know, again, I've not shown these experiments, but I can send you papers of all. So we have measured the kinking strength of these fibers, basically. And it's 300 megapascals. So it's not completely negligible. So people, you know, they make the assumption that this is like Kevlar with a, hello, have we broken up?
No.
No, we can hear you.
Or you can hear us.
Yeah.
But Zhigang seems to have disappeared anyway.
Oh, I'm here.
Oh, okay. So, you know, Kevlar.
Oh. All right. So Lihua, you can answer his question.
Okay,
he's back.
I'm back.
Okay, you're back.
Okay, so Kevlar, which is very similar, so an aramid like Kevlar has a kinking strength of 10 megapascals, but the polyethylenes have a kinking strength of 300 megapascals. I mean, they're not the same as carbon fibers, but they're pretty good. You know, 300 megapascals is not a bad kinking strength.
Yeah, yeah. Okay, so and so I'll make this the last my last question. So you did this impact experiment and simulation. Of course, many people also do this static monotonic loading contact experiments. So my question is just really elementary. So what's the difference between static contact and impact? So I can think of maybe inertia is an issue, maybe rate dependence is an issue. What is that?
So
make impact so severe.
Both are important, rate dependence and inertia, but at these velocities that we are discussing, Zhigang, it's inertia. So, you know, I mean, if you saw the simulations, you know, the end of the beam did not know that the middle had been hit, right? Basically, there was no, you know, there was a wave that was going through and, you know, you were getting all localized deformation. And this is the crux in ballistic resistance, is that you can't think of it as a bending string, basically, because you've not spread the deformation over the entire string. Everything has happened locally, basically.
Thank you.
You fail the beam, you fail locally before the rest knows that you know, anything has happened, basically.
You just gave a fascinating talk. Thank you.
Thank you.
Also very inspiring questions, Zhigang, which inspired two questions, related question of me. Then one question to follow up Zhigang's last question. Then depending on the loading rate, what are the typical impact experiment to do for those high loading rate impact?
So typical, what do you mean by, you want to think of an experiment that's simpler to do than a high impact, than the real velocity, or you think of scaling law? What are you thinking of?
Right, so for like static, right, for static you do like loading, unloading, but for high impact, yeah, usually I know like those Hopkins, SPAR, or what kind of typical experiments.
So there are different types
you want to quantify.
There are material experiments, which Hopkinson bar would be a material experiment to be doing. But then you see there's a big difference between a material property and a structural, dynamic structural property. And if you want to get hold of the dynamic structural property, you have very little choice but to do, you know, the sort of beam impact or plate impact experiments that we were talking about. Right. Now, some of us have tried to do, I mean, I must say unsuccessful, but I'll tell you what it is that these experiments are very difficult to do and, you know, to visualize properly, except, you know, these movies look nice, but I can tell you these students who've done these experiments have done 100 experiments to generate one of those images, basically. But what you can end up doing is, remember that it's inertia that we really want to capture. And if you end up designing a static experiment with a foundation, like a Winkler foundation, let's call it a Winkler foundation. A Winkler foundation can be designed to simulate the inertial forces that would exist in a given impact experiment. And that we have done. I'm not saying it works perfectly, but it works really usefully to get, because you can do much better measurements on Winkler foundations under static loading, and then you can, the measurements tell you so much more basically.
Right, but those experiments, if you are studying structure, then those are geometry specific, right?
Yeah. Now, so you have to come up, see, dynamic response is a structural property basically. So you have to come up with surrogate structural, you're not going to test your real structure, but you have to come up with surrogate structures that you can test in the lab. There's very little you can do. I mean, in some ways, that is what my theme of my talk was, that one is material properties. Now you have to go, if you want to go to structure, then you need to think of something else a little bit more than just material properties.
Yeah, then another question related to Zhigang's crash worthiness question is you at least mentioned two important parameters, right, or properties. Yeah, one is the energy absorption capacity, another is like the peak force. Then how about the energy dissipation, like the area between loading and unloading loop? That tells you, right, how much rebounds you still expect.
Yeah. Now, to be fair, I hadn't ever, because I'm coming from a very traditional kind of impact situation, I hadn't ever thought about these elastomeric structures. But hence, I'm not going to be able to answer your question in any sensible way. But that is something well worth considering. You have to be a bit careful that you don't want too much rebound, because rebound means you transmit more momentum, right? Basically, in the perfect case, you're transmitting twice the momentum that the incoming momentum, and that's the last thing you want. But it does have this capacity that you recover your structure, and it's a topic that hasn't been sufficiently looked at in the community, I must say.
Okay, thank you. Next, Tian Tang.
Thank you, Lihua. Thank you, Vikram. A very, very nice talk and very informative. I learned quite a lot. I especially enjoyed the mechanism, the failure mechanism map that you presented. I thought it was very nicely summarizing the findings. I have a question about length scales, because we're talking about structures. So there are a lot of length scales in the structure. Taking, for example, the last part that you presented, the ballistic loading of a composite beam. At the larger scale, you have the beam aspect ratio. I think you already addressed this when answering an earlier question. The Euler-Bernoulli beam is going to be different from the Timoshenko beam. The failure mechanism will be different. I imagine the size of the impact zone might be important as well. And at a smaller scale, you have the fiber dimension, maybe the volume density of the fibers. They might, I think, influence how the damage is evolving within the structure. So I was wondering if you could comment on what are the most important length scales in those structures.
Okay, so in these composites, in the very simplistic composites, which are just pure laminates, one of the most important length scales, which I've only showed one small image, which is the ply thickness. Remember that these composites are generating this so-called indirect tension mechanism, which is by shear lag. So the ply thickness has an enormous influence on that. So that is an extremely important design parameter that exists in these games, basically. The second, in some ways, the length of the entire beam is not a relevant parameter at all for practical cases. And why is that not relevant? Because failure occurs in a very localized place. The failure, if it has occurred well before the wave has reached the ends of the structure. So, the length, the overall size scale of the structure is an irrelevant length scale. So then you'd ask, which is the structural length scale that is most important? The structural length scale that's most important is the size of the impactor to the thickness of the beam. That would be, and in all the simulations, because I didn't have time to show all this, is that that ratio is extremely important, basically.
Okay, thank you.
Is that your answering your question? No, not really. I mean, I can see papers, where we have looked at, maps for all these different parameters, basically.
Yeah, I was just wondering, maybe you will have different maps when you change the dimensions, or maybe some dimension ratios.
Yeah, that's right. We have different maps and different. And this is the problem, right? There is no you can get an overall picture very easily, but the details require a lot of analysis.
Yes, absolutely. Thank you.
I believe Li Qing has one more question.
Yeah, thank you, Lihua. Professor Vikram, so just now when you answer one of the audience question, you mentioned that your experiment with the wet and the dry sands is similar to the volcanic eruption. So in the geology or volcanology field, this volcanic eruption is explosive or not. It depends on the silica, water, and gas. So if less gas, less water, and less silica, so then it will generate the kind of lava flow like Hawaii volcano eruption. So if we get more gas inside and more water and more silica inside the volcano, then it will get more explosive, like the volcano in the subduction zone, like that. So, but in your experiment, so you just show use the dry sand, you get less explosive, and then get more water, then you get the more explosive. Then you mentioned that the friction is the key parameter in these two experiments. So actually, in nature, the explosivity, it is not just depends on the water. It also depends on the other things. Maybe these things could cause the kind of chemical change, chemical kind of behavior, not only just the physical behavior. I just want to get your suggestions or comments.
So I should be very careful. When I said that there's an analogy between this and volcanoes, what I meant is that, of course, I was only talking about explosive volcanic eruptions, right? I was not talking about the non-explosive type. And the water in an explosive volcanic eruption is doing something to the chemistry of the explosion. Here in my experiments, the water, and in sort of a landmine explosion, the water is not doing anything really to the chemistry of the explosion, but it's only doing something to the transfer of momentum from the explosive event, from the C4 or the TNT to the granular medium. So when I say that the friction is important, I mean in that situation where the chemistry of the explosion is a given, and now we're only looking at the while I agree with you, in a real volcano, everything is mixed basically, and it's significantly more complicated. But there is sort of an analogy still, I would say.
You mentioned the key parameter. The water is actually one of the key parameters.
Yeah, water is but I think in an explosive volcanic reaction, the water is doing something more than just friction. That's what I'm trying to say. While in these cases, it's only approximately only doing friction, basically.
Thank you. Yeah, thank you.
Next, I receive a question from Salah Yu Ding. He is not able to ask the question, not able to turn on the video. Let me check whether, Salah, you can ask the question now. Otherwise, I will ask the question for you. Okay, if no, then yeah, Salah is a PhD student from Shanghai University. He mainly wants to comment that in the talk, comment on the idea that, yeah, for plant branches, it remain, as long as plants remain green, they have ductility. But when they're dried, so they become rigid and hard. So what if, yeah, we can add those bags of fluid into the material to enhance ductility of the material? Yeah,
I mean, enhancing ductility by, there's no question that if you do something like adding viscous stuff or something else to enhance ductility, you'll help. But I keep coming back to this point, is that the minute you do all that, you are creating a parasitic structure which can do your impact resistance, but can give you no structural capacity. Because if you can always increase ductility by increasing compliance or reducing stiffness, but most engineering people will not use such a material. Basically, they will insist that they want certain amount of structural rigidity to be able to use it. And so this compromise that we have to do, it has to be taken into account always.
Next, I believe Zhigang also has more questions.
One more question. So you, Vikram, you have made her impact so fascinating. I want to study it. Now it's an educational question. Now, actually thinking about my own experience, other people can confirm this. At schools, we typically do not learn about impact. We learn structure, we even learn creep, plasticity, shorty, elasticity, definitely, but not impact. I don't remember taking a single lecture, not a course, about impact resistance, right? So the question to you is, maybe I can ask you why, but the more relevant question now is, if I want to learn, or students, I'll make students learn, what is a learning material? Does the field has a classical review or classical book?
So there are two classical books. One is, because I'm in Cambridge, Bill Johnson. I don't know whether you've heard of him.
Yeah.
Bill Johnson wrote a book on impact mechanics, which I think is a very interesting book.
Yeah.
There is another book, but that is mainly to do with materials, which is interesting. The second book is an interesting book, which is by Norman Jones when he was at MIT before he came back to Liverpool. He wrote a book on structural impact. And that's interesting because it talks about all these structural issues involved in impact.
Norman
Jones.
Norman. Yeah. Okay, thank you. Thank you. Now, maybe a more general question about this. Why we don't learn this, not even in single lecture in school? Maybe single lecture is not useful enough.
Well, no, I think, Zhigang, it comes back to this issue, right? That it becomes very specific very quickly, basically, right? Is that it is very difficult to create general principles. And when we're teaching students, we want to teach general principles often rather than specifics. And it's very difficult to create general principles.
About impact.
About impact, basically.
Yeah.
And if you do, I mean, they may be, right? They may be hidden somewhere. John Hutchinson, wrote a whole series of wonderful papers where he tried to create general principles. And, even, somebody of his ability to simplify problems did not simplify it too much, basically.
Yeah. But just in terms of, let's say, not even scientific principle, maybe just typical experiments people would do to get impact data. What are these typical experiments? You described some, but let's make a short list.
I described some what I would call structural impact experiments. But let's go back to the first impact experiment, which was G.I. Taylor. The Taylor impact was the first and the most classical way to measure impact data. So starting with Taylor impact, then Kolsky bar, people at Brown, plate impact, Rod Clifton has made his entire career in plate plate shear impact, etc. So there's a whole series of what you could call material measurement, for high dynamic loading, basically.
But these are not inertia limited thing, right? It's just a material rate sensitivity.
No. You have shock effects inside the material, right? At these kinds of boards they're talking about, you get shocks, and you're trying to measure equations of state and things like that inside the material, basically. So you will have those kinds of experiments, and then of course the experiments that I spoke about, which are effectively beams, plates, and other kinds of things. These are motivated by applications. In some ways, all all structural impact experiments are motivated by applications. Norman Jones's book on structural impact gives a whole series of very nice experiments.
Thank you. Wow, Vikram. Beautiful.
Zhigang,
yes.
You didn't learn impact because you did not overlap with Vikram.
Oh, I didn't overlap. Yeah. I guess I didn't learn that because Jim and John were too busy with the fracture when they were young. And we were too busy taking their courses. I don't have time to take other courses.
MIT, as you know, Zhigang, has had a whole series of very important people working in impact mechanics. Not so much so in Harvard, because you guys work on far too scientific problems, basically.
Thank you.
Okay, next, Carlos.
Thank you very much, Lihua. Hi, Vikram. Very nice to see you again. I wanted to follow up on our conversation that we had. It seems like so long ago when we could actually have conversations in person back at Caltech.
Not 2D conversations.
Exactly. So hi, everyone. I'm Carlos Portela, assistant professor at MIT McKee. And Vikram, so my question, we've been talking a lot about, the structural properties. So my question is, so assume that we don't have a beam anymore, but we have some rigid wall at the back end of your plate. Does that mean that we're now turning this experiment into just a material response? And then the second question, and it's kind of linked to this kind of hypothesis and talking about the wave speeds. At that point, and I'm linked also with, inspired by the question on the auxetic response of a material. So for this auxetic material to work, we would need this projectile to be slower than the elastic wave speed. Otherwise, our Poisson's transformation could not take place ahead of this impact. So does that mean that if we have this kind of material test, do we need to be in the regime where our impactor is certainly slower than our elastic wave speeds?
So I'll answer that second question first. In a large number of situations, not in soft materials, I should say that in normal engineering materials, it is in most impacts are slower than elastic wave speeds. Elastic wave speeds are sitting in 5,000 meters per second, etc. Other than space impacts happening at 40 kilometers per second due to space debris, etc. On Earth, you're not usually thinking of more than few thousand meters per second, basically. So but I agree with you, the whole game will change if you start going to soft materials, because the wave speeds are so much lower in some of these soft materials, basically. And then you'll go into this hydrodynamic regime much faster, basically, right? Because the minute you go beyond that, you're going into a hydrodynamic regime. Now, with regards to your first question, that if you have a structure on a rigid backing and you're impacting it. Now that is a classic plate impact experiment. So that is true that you're measuring impact properties, the material properties at that point. But let me remind you of what I was presenting when I was talking about how high the structure jumps. So if you say to me that I design an experiment like a plate impact, where I'm just coming with another massive plate and I come and compress it, that is measuring an impact, a property which is a material property. But suppose I say to you that I'm doing a real dynamic experiment in the field, i.e. due to an explosive, basically. Then this fluid structure interaction, I'm calling it in general fluid structure interaction because it's interaction between a granular medium and the structure, or air and a structure, or water and a structure. Then you have to basically answer the question, how much momentum did I transfer into the structure? And that becomes a structural property at that point.
Right. That makes sense. Okay, and I guess kind of quick follow-up. So then assume that we have a structural experiment. And I'm thinking of something that's very ductile, and where you have some spherical projectile hitting it, but the damage is actually very localized. Yeah. At that point, what's the limit for us to start considering that no longer a structural experiment, but rather just a localized response of steel or something like that, or is it not?
At a very simplistic level, if you tell me that. So let's come up with, suppose you tell me that it takes time t to stop your projectile, okay? Mm-hmm. I can ask the question, how far did the elastic wave travel in that time, basically? So I will get two length scales. I'll get a length scale which is regards to how much I've penetrated, and a length scale regards how far the elastic wave has traveled, or plastic wave, whatever you want to think about it, in that time. And if you tell me that those two length scales are very comparable, then I will call it basically a material property that you've measured, because you've not done anything, you've just done something very localized, basically.
Okay.
And if that is not true, then I will say you have to start thinking of structure at a very broad level, right? I'm trying to get very simplistic back of the envelope rules, basically.
Right. Right. Okay. Thank you very much, Vikram. Very helpful.
The next, I believe Robin has more questions.
By the way, the panel, Mattia Bacca has nicely reminded me that my close Cambridge colleague Bill Strong has also written a book on impact mechanics, G-Gang. I should not have ignored that book. You know Bill Strong, of course, G-Gang, right?
Yep.
Robin, go ahead.
Okay. Thank you for all the discussion. So Zhigang, unfortunately, I didn't learn anything from you or Harvard for impact mechanics. But say something about Caltech. We had a course on dynamic behavior of materials or impact mechanics from G. Ravichandra, of course. So I said in it last semester. It was very nice, and I learned it's both theory and experiment. The textbook, I believe, was from Mark Mayer on dynamic behavior of materials. So and also I think from the SEM society a community, as Keqi mentioned, there's the broad community on this. But so the question for Vikram is more broad, so more general. I know you also are now an expert in biomechanics. How do you maintain the crosstalk, especially among students, between these two topics, education and the research? Thank you.
So you mean to say, how do I
say? I'm just wondering if now it's returned to us as maybe Carlos and I, we both junior faculties. Like we want to approach different topics. Say in your case, biomechanics and dynamic behaviors or composite. Then it seems very challenging, right? So you probably have this student and that student. How do you keep them both talk with you maybe effectively, or even just maintain the crosstalk between themselves?
Well, you know, I don't need to tell you, because you work with Zhigang, who works with so many different topics. You know, so I'm not sure I maintain it successfully, but what I'll say is that the principles, at least, you know, I mean, whichever topic I work on, the principles are approximately the same. Now, the details change dramatically, and you need to do background reading the details. But the laws of physics, you know, and thermodynamics, etc., which is true, very important for biomechanics, don't change whether you're looking at steels or you're looking at soft materials or you're looking at biomaterials. You know, I mean, so that is what I will say to you, is that, and in some ways that answers the education question that Zhigang was answering. Why it's so important, I think, is that in education, we should not teach specifics. We should teach general principles, because then if you know those general principles, you can pretty much go and do whatever you want later on in life, you know, so that's, I'm not answering your question, but that's what I'll say.
That was very inspirational. Thank you.
Yeah, I believe I have finished the question list, but let me see whether there are more questions from the panelists.
Yeah, Turn has been quiet.
Yeah.
Turn, you always have a question. Turn, by the way, is a movie star in China now.
So actually, I had a similar interest on this trustworthiness in vehicle. So you mentioned about this energy absorption plus the stress felt by the passengers or the drivers. of the vehicle. So in that sense, it means that the so that allows the time to chip in, right? Because the stress we feel is essentially is the acceleration the human body experiences, right? So how to mitigate the acceleration becomes critical. Not only the energy you absorb. So yeah, I thought is that the essence of this trustworthiness design of the vehicle structures, especially the different side and the front portion, to mitigate the energy and also mitigate the acceleration.
That's absolutely correct. Is that what you're trying to do? Is you're trying to spread it in time, basically. The momentum that you have to kill is the same, basically. And so the issue really is, if you do it over a long time, then you're reducing the acceleration, and then you're reducing the injury to the passenger, basically. And it's sort of interesting because all cellular materials will never be as efficient as a solid material if you just use energy absorption as your metric, right? Because by definition, a solid material will always, per unit mass, absorb more energy than any known, well, by definition, right? By bounding theorems, basically, will tell you will absorb more energy than any architected material. But the reason you use an architected material is because of that you can actually design the stress level so that you're stopping the amount of, you're reducing the acceleration to an acceptable level, really.
Yeah, that's actually, I think that's a very interesting discussion because during the Q&A session, there were a few occasions you mentioned this more fundamental research study versus the more practical applications, and like the engineering material design, right? So we look into the mechanisms to strengthen the materials, toughen the materials in real application, like the vehicle design. It's by the end of the day, it's sort of a compromise of different things, right? So, and also we don't even talk about the cost here. And I mean, Ashby spoke there are the cost issue there as well, that the economic factors there. So that's actually, I think it's very important as well.
As we go on in architected materials, is that this issue that if you want them to be used, some of these issues will have to be considered as to, that we don't want to optimize on one property. That is exactly how engineering materials are not used, basically.
Yeah, because we work with, try to work with automobile industry and start to realize it's a very conservative industry, and that it's not that as excited with the scientific advances as there were many considerations from their side.
This is going beside the point, but the reason why I have focused on applications, which are these military applications, is partly funding, but partly they are willing to take more risks than the automobile industry. The automobile industry will take no risks, while the military people will take risks in terms of
For military applications, the saving, for example, the lives of the soldiers, it's more important than how much the vehicle should be. I totally agree with you.
And also at university or basic research institution, you probably want to study individual properties well enough, so you have some basis to do overall optimization. As just Vikram just said, just show what's happening first before you even start to optimize.
Yeah.
Right, individual properties are interesting.
Then if you have
limit, right? If you push a limit, then the design space is much larger. Then when the engineers, when they design things, then they come up with more better designs there. It's like pushing the Ashby plot.
So Now, actually, the talk about an actually plot. So we plot modulus is an axis, density another axis, right? And the strength, the toughness, these are axes. Impact has no axis or too many axes.
Too many axes. That's the problem. Impact has too many axes. That's the problem.
So you know, there's an American saying, probably universal saying, if you don't measure anything, you cannot optimize it. If you don't measure it. Or you measure too many things, you don't optimize either.
That is unfortunately the case.
Okay, Lihua, our leader, what do you think?
I think that's wonderful. Do we have any more questions?
Yeah.
If not, yeah, I really like to thank Vikram for this very inspiring and informative talk, and also thank all our audience and panelists, especially those who have been with us for almost 3 hours. Thank you.
Actually, I have one last short question about Lihua. Lihua is our host today, gracious host, fantastic. I actually did not know you work on impact yourself. Just quickly, how did you get started?
Yeah,
Lihua work on impact, unbelievable.
Yeah, we are still in a little bit slow rate now, not go to that like shock regime yet, but we're interested in energy absorbing materials, especially by like structure design, those energy absorbing metal materials.
Okay, thank you.
But hopefully later I'll learn more from Vikram.
Okay, Vikram, thank you.
Thank you. Okay, bye.
Thank you.
Bye.
Bye.